talking about still. We have introduced a couple of things. One of them is that we have some prediction on the number of counts we expect, and we have a likelihood, which is the Poisson kind of distance between our prediction and the actual data, and we try to maximize this likelihood or maximize this posterior distribution. So if you look in a physical parameter space, we have maybe luminosity and temperature. This likelihood, then you can interpret it as kind of a hill, and we try to map it out. And these are some algorithms we will talk about now. This works. And we will talk about algorithms to explore this, so we can constrain these physical parameters. And what we're going to start with is local optimization algorithms. Take it away.
I have two.
You have two.
I got upgraded. So, talking about local algorithms, the one that you will all have used, if you have typed in fit or fit counts in some spectral package, is called the Levenberg-Marquardt minimization. This is what XPEC is using. This is also what ISIS is using. This is also what Sherpa is using. The advantage of Levenberg-Marquardt, some people call it Powell's method, but the advantage of Levenberg-Marquardt is that it gives okay results, and that's why it has been the single choice for people in the field up to the time when computing power got cheap. So, last 5 years or so. You'll see that all the other methods that we've been talking about are much better because they give you real information. This one is good enough to get a quick result to see what's going on, but it also has some pitfalls. So what is the fitting problem again? I was briefly just introduced, right? This is what we were trying, what I introduced earlier, what we talked about. In the linear model, we have some way to take a model and a physical, astrophysical model and predict what the data look like. The model can be something that's empirical, right? If you have done X-ray astronomy, somewhere in your brainstem, you know that if you load a data set, the first thing you will be doing is probably, if you do continuum, type something like TB ups times power and fit, and after that you start thinking. If you type FUPS times power, it's okay. If you type WAPS times power, you should be short. You can ask me later why, but yeah. But you should commit suicide. Right? So what you have is, or you have a very complex model, something that includes, for example, all of the physics of the object that you're looking at, a combined photoionization plus collisional ionization model that as parameters has elemental abundances and temperatures and gradients and things like that. So this is this function here. We know how we can predict what comes out, and then we heard previously that we have some kind of a fit statistics, the likelihood, and we want to know what is the most likely mode. So we want to vary these parameters here that describe the physics of the model and vary them until we get something that looks as much as possible as the data. Okay? And we do this using the statistics that were introduced before. Now, for historical reasons, for some, right, you want to maximize the likelihood, but all of the algorithms that are used to do things come from mathematics, and mathematicians, interestingly enough, always studied minimization. In other words, you want to fit minus the likelihood, for example. Or you want to minimize the deviation between the data and the model if you have the Gaussian chi² thing. So this is a minimization problem, and therefore all of the algorithms that we use in practice are minimization algorithms that are derived from mathematics. Okay? The easiest minimization algorithm is essentially this one here. This is called a gradient method. It says for each data point, you have the difference between the model and the observation. You normalize that difference in some way. Okay? And you do this to get a vector of residuals. And now what you're trying to do is you want to minimize your fit function. So the thing is you want to calculate how does the fit function behave, how does the fit function change. And if you think of the fit function as a hill or as a valley, depending on whether you talk chi² or Bayesian, the logical thing to find the minimum or the maximum somewhere is you walk along the gradient, so you walk up or downhill. Okay? So mathematically, what do you do, therefore? You calculate a gradient vector, just take the value and then you use the Jacobian matrix, which is just the derivative of the residual with respect to your parameters. We have at least one mathematician here in the room who will not like that notation. I apologize, but if you're a physicist, you notice that this thing does not have a series around, so this definitely is a matrix. And since this is a vector down here, because it's bold-faced, this thing is a matrix, okay? So you have a big... Sorry, Max. Okay, so you can then use this and essentially check for where is the gradient. Oh, it goes down here, so you walk in that direction. You calculate your likelihood, or your measure of goodness of fit. Again, if you see, okay, it has decreased, then you say, okay, well, this direction is okay. You re-evaluate the gradient, you take the next step, and so on. This is standard way of finding zeros or minimizing the function. Problem is that mathematically, the convergence of this type of method is not very good. And the reason for this is that if one looks at the properties of this matrix here that we use to find the step in our parameters, the method is not very convenient. Effectively, what happens is it walks down the valley, goes up, goes back, and then oscillates back and forth. This is fine if you are applying it to a very simple problem. It is not fine if you are applying it to a real problem where, for example, the computation of your model here might take a second or two. I've been working with models where the evaluation of one model run took 15 minutes, and then suddenly you're talking here about months of computer time. People realized very early on that you can improve on this method, and this is what's called the Levenberg-Marquardt method. This was first invented by Levenberg in 1944, then forgotten because in 1944 computers were not really a thing, and then rediscovered by Marquardt, and since then this has been the standard method of choice. The idea behind the Levenberg-Marquardt is that you really push this idea of the gradient. If you look at the math here a little bit more in detail, what you're really doing is you calculate an n-dimensional curvature in space, and you walk along that curvature, while you really should, when you're far away from the hill, just say, okay, yeah, this is the gradient, let's walk there. And only once you get closer and closer to the maximum or minimum, you should start thinking, okay, I should probably turn a little bit left and right and go, where's the flag on my mountain, okay? And this is what Levenberg-Marquardt effectively does. The basic idea was, rather than using the so-called curvature matrix, you try to emphasize the gradient. Okay? So what you do is you do this calculation here as before, and then you multiply the diagonal elements of the matrix by some number, or you add a number to this. So by just taking the diagonal elements of the matrix, this matrix really is will look more and more like the gradient. Okay. So far away from the minimum, you are dominating by the diagonal of the matrix. Therefore, you walk along the the gradient, and then this should be the unity matrix. Sorry, and then as you get closer, you then start to change this value lambda until you get more and more in an area where you can describe the shape of the function that you're minimizing by a Taylor series of first order. Okay, that's effectively what you do, right? Again, this is physics. What do you do if you don't know anything? You Taylor. You cut off after the first element. You see how far you get. Okay. So Levenberg-Marquardt algorithm is this, and is a prescription on how you change this lambda here. And the way how this is done is that if you get closer to what you think the minimum is, you switch over to the curvature matrix. If you get farther away, you get closer to the gradient. Okay? And built into the method then is you check at what does the so-called sum of squares look like, and the sum of squares is nothing more than taking this thingy here, squaring it and summing it up. Which, if you listened before lunch, this is chi². Okay? So, if it decreased with respect to the previous step, then you say, oh, I'm probably closer to the minimum, and you reduce your value of lambda. If the sum of squares increase, then you say, oh, I'm walking in the wrong direction. Let's not walk in that direction. Let's increase this value of lambda and try again. Okay? And so what you see when you look at what happens to the fit in XPEC, or if you're using ISIS, you switch on the fit verbosity, you see how this leads to a path through n-dimensional space that in the end approaches to a minimum. Okay? And this is the first problem here. In principle, this method works very well whenever you have a function, a fit statistics, that has squares in it. So something chi² like. One can prove that this method fails to converge or converges to the wrong place if you have a fit statistics that does not behave similar to sum of the square. In other words, Levenberg-Marquardt is not guaranteed to converge whenever you use C-stat or M-stat. Okay? Which doesn't stop most people from still using it. Yeah, but that's a different thing. You have probably all used it for that. In most cases, it works, and you will think you have convergence. And then, if you use a better method, you realize, no, you haven't reached convergence. This is why, if you're an X-ray astronomer, right, you do your first thing, then you calculate your errors by typing in the error command in XPEC. What the error command then does is it perturbs the fit by changing parameters in the fit statistics, and that will usually then bring you in another area, and then the algorithm runs away again to another random area, and then you repeat this a few times, and eventually it gets even if you want to go home and you say, oh, it's converged. For simple cases, and if you are in the Gaussian regime, this works well. It generally also works well for faint sources because your background dominated there, lots of constant there, but that's it. The second thing that's important to know is that these numbers, group and boost, are religion. Depending on the different implementation of Levenberg-Marquardt algorithms, people use different parameters there. None of these combinations of how far should you go, should you decrease the number, and how far should you go up, will help, will work for all cases. If you have software that allows you to change these values, it is useful to change those, usually. This means if you use expect, you have no choice, rather than to believe that Keith Arnaud decided was correct. In other software, you generally have a way to change things. I recommend to you reading a paper by Lambton from '97 about this, which explains in very nice detail with very complex minimization problems on how this works. So this is the method you all have been using. It converges sometimes and for simple cases. In real physics, you will do this to guide your thinking. And once you have done that, then you should be using proper, better algorithms that, for example, ensure global convergence, global minimization methods, and methods that work also for cases where chi² should not be used, which really is for most cases.
I follow what you say in the case of one parameter to change. But if you have multiple parameters at the same time, lambda has to change independently for each of them?
You use
the same lambda.
Yes.
But if the parameters have a different weight, or they have different way of changing, having the same lambda for each of them can affect you.
Yes, and so that is why there are two ways of doing things. One is called multiplicative damping, and one is called additive damping. What is usually used in many pieces of data analysis packages is multiplicative damping. I was jumping over this a bit too fast, perhaps. The idea really here is you very much emphasize the diagonal matrix, and one can show if one uses a method like this, you precondition the matrix. Because what you're doing here in this step is note that the decision on how far you change your parameters depends on the inverse of the matrix. Okay? And preconditioning means that you make the matrix more diagonal, so you make the eigenvalues more well-behaved. And that means that the computation of the inverse of the matrix works better. That's why many people use this. You can also use this. This doesn't do, additive. Sorry, I was talking about, many people, use additive, not multiplicative. If you have matrices that are more complex, then usually with multiplicative damping, you can play by, depending on what starting value you do, to change your parameters. Okay? That is one of the problems of this minimization method. And if you ever wondered why spectral fitting packages have these weird normalizations, this is the reason. So, for example, what you are trying to do is you're trying to make all of your parameters against which you calculate, against which you change, you're calculating here the derivative and so on, and you want to have all of the values of the derivative approximately of the same order. If you have a matrix that is dominated by a few values, then this whole inversion will be dominated by these values, and that will completely drive the way in how the algorithm converges. If you want to try this out in a simple case, if you use TB-APS, the only real absorption model, unless you need to use this, because you have ionization in the interstellar medium, the full absorption model has a simple way of proving this to you. There is a version that's called TB-ARFs of the interstellar absorption model, and that allows you to change all of the abundances of individual elements. If the value is positive, as it usually should be, that value will be the relative abundance relative to a solar set. And the reason why I chose this as the default value is that this makes all of these parameter values around unity. If you take the value if you set the value to a negative number, it will be the column of a given element, which means it should be on the order of 10 to the 19 to 10 to the 22 for typical conditions in the interstellar medium. And with this, you can produce a matrix that has unities somewhere and then 10 to the 20s somewhere. This will kill this method in like no time at all. Okay, so you should, whenever you develop a spectral model, rule of thumb is that for this to work, and I think also for MCMC methods, but they're less badly behaved, I think is the whole statement. No,
You should always.
yeah, so I got lucky.
You should always normalize that.
Choose your units such that they are roughly 1. Okay? If you're a proper astronomer, you'll probably do this anyway, because as an astronomer, right, we all can work in the number range between -100 and 100. Everything bigger is nothing that we do in astronomy. Right? We change units rather than make larger numbers. But you should also do this because otherwise you cannot use the model. Thanks for the question. But the basic is inversion of matrices with very large differences in the matrix. Don't do it. That's Levenberg-Marquardt.
So are you aware of any some kind of computation we discussed that? Because it's nice that we have it in here, but when we go on and
So the whole, so in my opinion.
what are we to give our students to read?
Okay, in my opinion, everybody should read this article here, especially the first 1.5 pages, and then the last paragraph. So read it like any paper, read the introduction and the conclusion, and believe what happens in the middle. And that's for practical work. That's good for the conditioning. Any book on numerical analysis will tell you.
And if you insist on doing maximum likelihood fits, yeah, if you insist on doing maximum likelihood fits, there's also 3ML, which you can use MUA or any number of other minimizers besides Levenberg-Marquardt.
So what we do, for example, in Bamberg very often with ISIS, is we'll be using, in ISIS the big advantage is that you can switch between 10 different minimizers, and you can add more in there. So I generally find that Levenberg-Marquardt is pretty good if you have no idea what happens. Right? So you use physics, your physical condition, your physical intuition with the Levenberg-Marquardt, and you generally will end up with something that's not completely stupid. And then you switch over to methods that are better, but at the same time also generally tend to require many more function evaluations than these methods. Okay? The reason why these are good, well, the reason why people like those is that you get an answer in a finite amount of time. Yeah, but it starts to be really complex once you then need to look at the parameter space, and that's next. Or are there further questions?
Yeah, I was thinking, I don't know if there is any example of how these difference between methods for minimization affects physical parameters that we are using as resource. I mean, because people are publishing, as say, whatever method they
I think we'll be seeing a few later.
Okay, I can just give you an example. Between Levenberg-Marquardt and something like Minuet, you can fit a really weak spectrum, just a power law, and it will converge to completely different places.
Yeah. Unless you switch Minuet to the Levenberg-Marquardt rule, and then it converges to the same, and that's also good, by the way.
But I also, just as answer here, I've also seen publications which compare the results of different minimization algorithms, just point out that they are model dependent. So I think this might be a good idea.
My impression is that the number of such publications, at least in X-ray astronomy, is very close to zero.
Like people also never state which minimization algorithm they actually use. And it's kind of like one big vibe I have with that. Like, well, I I use minimization. Well, are you using the standard expect minimization? Are you using the standard minimization or whatever you're using, whatever software package you're using? Did you change anything? And people just don't stay there.
So, I know this from particle physics, so whenever there's different algorithms, it's stated compared to the results.
Yes, and the reason there is that in particle physics, all people use min-width. The problem with this, if I may add to this, is that min-width is about state of the art of 75.
And there are giant differences, not only between minuet and minuet 2, but different implementations of minuet 2. The Python version of minuet, which is minuet 2, will converge to a completely different place from the C++ version, because wherever they're fiddling around with the matrix, they do something completely different in the source code.
So expect, for example, tends to put a lot of work into the matrix routines. That's why it tends to be fairly stable. I find it's generally comparable to min-width in most cases I've worked with, which is a subset of sources. I have, for example, noticed that I'm lucky in that I usually have lots of continuum and a few lines, which is nice. My experience with collisionally ionized plasmas, for example, is that I've yet to find an algorithm that really works if you have something that has high signal to noise. The reason why this hasn't been noticed by the community a lot is that we are lucky that the effective area of current instruments is low. However, I run into this, I would say, quite a fraction of the time that I have for science whenever I do simulations for Athena. And there, for example, with this approach, we'll come back also to the binning a little bit later. The approach that we're using right now is guaranteed to fail. Okay. Hopefully, in the 10 years, the computers will be so fast.
Two general points. These optimization algorithms are heavily studied all across science and by mathematicians. And they have developed dozens and dozens of methods, so we shouldn't confine ourselves necessarily to the three that are the favorite of astronomers. And there's a lot of studies out there if you look a little bit beyond. Right, so that was local optimization just by a few examples. Now I'll explain a little bit about MCMC. I think. Let's see. This works better if it's moving. Right. Oh, yes. So before coming to that, now let's say we found with our minimizer the best fit. What do we do with this? Well, so what you actually want is you want to constrain your physical parameters to some ranges. And what we usually want to, or what many people do, is they want to have some confidence interval. So I will just explain what a confidence interval is very briefly. So let's say you have your physical parameter here, and you found your best fit, and your best fit is 0. And now we will make a couple of assumptions. Let's assume, the curvature here is the likelihood. Here it is plotted. Okay? So you found your peak, and then it decreases to both sides. And now we'll make a couple of assumptions. If this likelihood function is away from any parameter boundaries, so it's nicely isolated, and if the model that you're fitting is linear in its parameters, for example, you have components that are additive, and if the number of data is high, so you have a lot of counts, so that you have this symmetric, nice, single Gaussian distribution. If that is true, then you can do the following. You have the best fit, and you imagine that you generate a whole bunch of data sets with that best fit as the true input value. all of these data sets, you find the best fit. You optimize their likelihood functions. You get all of their best fits, and you construct a confidence interval, which is you go to their best fit, you go down by 1 unit here in log, you go down -1 on both sides, and that will be your interval. Now the idea is that all of these confidence intervals will contain, let me see if I get this right, all of these confidence intervals that you build now will contain 60% of the time the value you put in. So the assumption is you're away from the boundary, the model is linear, the number of data points is high, and the best fit that you use to simulate all of these many data sets is the true value out there in the universe. That's what a confidence interval does. And that's what we quote when we say this parameter plus minus something. That's what it is. Was that a question we wanted to ask in the first place? Are these conditions what we are happy to assume? First of all, our models are usually never linear, and the number of data points is basically never high. That's also why you often find these asymmetric errors quoted, which tells you these conditions are not valid. And we don't want to assume that the best fit is really the true value out there. So, what do unequal uncertainties on confidence intervals really mean then? If this 68% of realizations is not what we state here. If those conditions are not valid, you can still proceed and make confidence intervals. And you do that by actually performing these Monte Carlo simulations. So you take some parameter, you assume that's a true parameter, you make a whole bunch of simulations, and look how your best fits are distributed. And that will tell you how your analysis process is behaving under similar data as the one you're assuming. And so you might get out a probability distribution of your best fit parameters, assuming you put in this parameter, and then you know kind of the response of your analysis process. And so this is called parametric bootstrap. You just simulate data sets and you fit them and see how your analysis procedure is able to recover them. That's generally a good idea. And one particular case that's kind of special is if you put in that input parameter is 0, for example, some component is not there, but then you fit it with that component enabled, then you might, because that parameter is probably positive, its normalization, it will probably be not exactly 0, but will have some distribution, and you can ask how many of those data sets that are simulated which don't have the component, how large will the contribution, my best fit parameter for this component, be at most. And then you can look at the tail of this distribution, and if in your real data set you measured something way higher, then you can be confident that this component didn't arise by chance. We'll hear more about this later. So then you found your best fits with some minimizer, and you have, for each of your data sets, let's say you have a sample of objects, you have your best fit and some confidence interval. Okay? If you have multiple of these objects and they have different data constraints, then these confidence intervals are of different sizes, right? So what do you do with this? People often make just histograms of what the best fit parameter is. Now that this is dependent to how your best fit, where it lands depends on the data quality. You have basically a convolution of your true parameter distribution, how they are distributed out there in the universe, convolved with how well you were able to measure it quality of your data, and also your analysis procedure, which could be where your minimizer happens to land. So this histogram of best fits is kind of amalgamation of analysis procedure and distribution out there in the universe. A little bit better is if you make cumulative distributions, but it still has the same broadening of your analysis distribution. And so what's the meaning of these distributions of best fits? What happens if you have upper limits, right? How do you incorporate this? A clean way to do this and look into this is to model this intrinsic distribution and your measurement process. And one expression of that is modeling the population distribution with hierarchical Bayesian models, and we'll hear more about that tomorrow, I think, possibly. Yep. Right, so we heard about minimizers. Now I'll talk about sampling, and in particular MCMC. So I said before, we have some likelihood, and we have maybe prior distribution, and we want to identify the regions which have most of the weight on the parameter probability. So we want to find the regions that have most of this posterior mass, where most of this probability lies. And the idea of these sampling procedures is that you sample proportionally to the height of this distribution. So you get samples out that are denser where the surface is higher, and less samples further away. But a very simple way to think about it is, if you have this, you just make a grid here, you evaluate the likelihood at each point, and then you have for each of these grid points, which have a width, which is prior volume, you have a value, which is the likelihood, and multiplying them together, you have the posterior. Right? So you could just do a grid, that would be fine. But there's a little bit of a, yeah, so you could make also in a 2D space, you could make a grid, evaluate the likelihood at each point, and then look where in this parameter space you have 90% of this probability. And that is exactly what we do when we say we do parameter estimation. We try to find regions where most of the probability lies, and we ignore the rest. Now there is an issue, because how you define a grid, how you define the spacing in the grid, is different depending on how you choose that parameter. If you choose the logarithm of that parameter, spacing is different. In other words, you can also see it this way, it depends how you define which regions of your parameter space are larger compared to other regions. There is no unique answer to that. And this metric of the parameter space is what Bayesians call a prior. So you can look this grid or this grid, and your answer might be slightly different, and it's interesting to check how different the answers might be. So in Bayesian inference, the word is not confidence intervals, but credible intervals. And the credible intervals are an interval that contains so much percentage, so much probability over your parameter space. So for example, you find an interval which contains 90% of the probability. Okay? And there are a couple of definitions. You could start at the peak, you go down, you make it larger and larger until you have 90% of that area. That is called the highest density interval. Or, now that this is a probability density distribution, you can also make a cumulative plot of this, and then read off the quantiles. So you could read off the 5% quantile and the 95% quantile, and that contains 90% of the probability. I usually do that. Or, if that probability distribution is bordered on one side, you can just quote one quantile, which is kind of an upper limit to that parameter. One point here is there's no unique definition, because it's just where 90% of the probability is, but you can choose it differently. Just have to be clear what you mean. Most of the time it also doesn't matter. Okay, I will skip this. Right, so this is with grids. Grids don't work because if you have, let's say you make a grid with 10 points in one parameter and 10 points in another parameter, and you keep going and adding parameter, then you will have k to the d points to evaluate, and that quickly becomes infeasible. It's called the curse of dimensionality. So we need to have smarter techniques and go explore the entire parameter space. And one neat way to encode this is to sample at different locations in the parameter space. So you have samples in the parameter space. And one cool idea is that you sample such that you get the samples proportional to the probability, what I was mentioning here. You have this curve that you're trying to understand, and you have samples where the density tells you about the curve. So you get these posterior samples out, they could be weighted, so they could have a weight, and these are some techniques which allow you to explore the parameter space that way. And if you have these samples, cool things you can do with them is, if you have these samples, you can make histograms, which then approximate the probability distribution. You can make quantiles of these chains, of the visited points. For each parameter, you can get the, you can sort them, throw away the lower 5% and the higher 5%, and the middle part will be 90% of the places that you visited, which is 90% of the probability that is in the posterior. So you can find regions with the highest probability. You can also compute probability of regions. You can ask, well, how much of my chain is above a certain value? And that tells you the probability of a parameter being this large. And you can, because you have this chain, you can make computation on each chain point, maybe predict some other model, overplot it with your data, and then you have a whole range and an ensemble of predictions. And you can derive parameters. So here I have a chain where I fitted for some normalization and the redshift, and I get, I plot here luminosity and redshift. And you see each point reflects one of these posterior samples, but now in a transferred space, and I get a posterior distribution on these other parameters. So these are things you can do with posterior chains. Now, one technique is importance sampling, which is not very well used in X-ray astronomy. If you have some function that you are trying to understand, but it's not analytic, you can't find the mean, the peak, and its location, because that's what you're trying to learn. You put in another function, which kind of looks similar, but is analytic. So you have this proposal distribution Q, and then what you do is you draw according to this proposal distribution, and you weigh your samples by the ratio of the densities between those two distributions. So you will get more samples here, but you will correct for that by the weight, by the ratio of the weights. And so you'll get a weighted chain, which you can then reweight if you want. The advantages of importance sampling is that it's quite efficient in low dimensions if you have a function that approximates your true function well. You can parallelize it very easily, and you can integrate the entire parameter space. Disadvantages are you need to find this good proposal function. There is variational Bayes, which is a technique to optimize your proposal. And this technique has relatively poor scaling to high dimensions because your proposal is not perfect and then your sample is a bit off. Another technique, which is much more common, is Markov chain Monte Carlo, and the idea is the following. You start at some random point, and you do the following loop forever. You are at some parameter, you draw within your vicinity with some normal distribution. So you have some surrounding, you jump somewhere, put 1 foot there with some proposal, and then you check. Is the ratio of your new point compared to your old point, did that go up? If it went up, you go there. If you went down, then this value is less than 1. You accept still with the uniform distribution between 0 and 1. So you're allowed to go down sometimes. If you accept, then the new parameter where you are is this proposed parameter. And then you add where you are at this time step to your chain. And this chain that you're building up in these loops, the idea is then that this chain has these properties that we said before. It's proportional to that probability distribution that you are sampling. The missing ingredient is how you jump in that proposal. And that you have to put in, and that differentiates many different Markov chain Monte-Carlo MCMC algorithms. If you don't put any target distribution in, if you put in a flat distribution, this process makes a random walk. So all of these chains start out here, and you see how it diffuses across the space. Here a 3-dimensional parameter space. So if you don't have any constraints, this is what it looks like. But if you do have constraints, then it will target towards that, sometimes diffuse away from it, and come back to it. Here are some of the most popular proposals that are used. The first one is the one I just presented. It's called Metropolis proposal with a random walk, where you just have this Gaussian jump, which you can optimize to give you better acceptance rates. Another very popular one is Goodman-Weir proposal, which works the following way. You have, instead of one sampler, you have a whole bunch of samplers. And the idea is that these samplers learn from each other. And the way they learn from each other is, if you try to update this point, you find another point, and you take the vector from one point to the other point, and you propose in that direction. So you kind of get the direction and the length, which tells you something about this, basically the degeneracies according to your volume. And the neat thing about it is that it automatically learns the distance scales that you have to jump in various directions. And it works quite well for Gaussian constraints. So if you have these kind of ellipsoids, and your walkers start to sample these ellipsoids or these Gaussians, and they know which direction to preferentially jump to. And this is quite common in XSpec as well. A more advanced algorithm is Hamiltonian Markov chain Monte-Carlo, which I'm going to show an animation of now. So this is the random walk with MCMC. So you see it jumping, proposing, and if it's red, it doesn't accept, and if it's green, it does accept. So sometimes it jumps. And the idea is that you build up this distribution of points that you see here. If I let it go faster, jumps around. And ultimately, the idea is that you can make these histograms of one parameter, a histogram of another parameter, and this approximates then this underlying distribution, which you can't analytically solve for, but solve for with this chain. You see it's a bit slow. The Hamiltonian, the difference is that it uses the gradient information, so it tells you that the gradients tell you how easy it is to walk. If you imagine a marble on a surface, how easy it is to walk, and it makes much longer jumps. So the samples are much less correlated. And if I speed that up, you see the distribution is actually, it also went all the way out here because the jumps are longer, and the distribution comes to the true distribution much quicker.
How does this scale with the number of function evaluations?
So the difference is that the Hamiltonian MC also uses gradient information. You don't just evaluate the likelihood, but also the gradient of how sensitive it is to real parameters. And so that is often quite costly, if it's even possible to implement, because you need to have derivatives of your model. And so if you can do that, it's more efficient. If you can't have derivatives, then you can't use it.
No, but you can use, I mean, like in STEM, you can use auto.
You can numerically differentiate it, which is very costly.
Yes, it's very costly, but the effective sample size, so the number of non-correlated samples from Hamiltonian and uncorrelated median, almost extremely high compared to regular non-correlated. So in other words, that's kind of cool.
Yeah, the issue really is that so there are techniques to derive gradients from code where you don't have to do it by hand, but it's really the gradients of the model. So if you have legacy code from Fortran or something, it won't autodiff that for you.
Well, I mean, most models,
If the model is
radiative
somewhat
transfer can't be differentiated, right? So as soon as you start with a physical model, you essentially have to do the numerical differentiation.
yeah, that's what I'm saying. It's usually a bit, can be difficult, but for some models you might. Okay, so advantages, disadvantages. This one mixes really poorly. It explores the parameter space not very quickly. This one is nice because it kind of auto-tunes the distribution of points to, if you have a Gaussian likelihood shape. But if you have bananas, then because it's doing straight lines, it's not doing so well exploring the corners. And there's also a paper that shows that if you go to very high dimensional parameter spaces, let's say 50 to hundreds of parameters, then because you're doing linear combination at some point, this population of walkers collapses to a surface, and then you have a problem. And HMC is very nice because it auto-tunes itself to more complex surfaces, but you need gradients. So we don't usually apply it. So when do you stop MCMC in the first place? So because I showed you the code with the infinite loop. So there is very deep theory to MCMC, and it's quite well understood how it converges. But the convergence are, and if you let the number of samples go to infinity, and usually we only have finite time. So what can you do to identify now my chain is good enough? One thing you can do is you plot the visited parameter over the iteration. That's called a trace plot. And if you see a lot of structures, so it kind of wanders and then wanders down again, then what you're seeing is that this diffusion is still exploring some part of the parameter space, and you still have correlation, so you probably want to run it quite much longer. You can convolve these trace plots with itself, so you take the visited parameter, shift it by 1, shift it by 2, shift it by 3, and you get the correlation. And that usually looks something like, if you have zero shift, you are 100% correlated. If you shift it a bit more, you get still some correlation because you remember where you were just before, but then it decreases and decreases and decreases, and how wide, how fast you forget where you were, that's part of the autocorrelation length. You want to run your chain many autocorrelation lengths, so you forgot your initial start. Because also you can think of the lifetime of a chain as you start somewhere and then it wanders up, and then it discovers where it wants to sample. You're more or less the peak, but then you still need to explore the entire surface of where all your probability lies. So you can have this identification phase where you go to your hill, and then you walk around the hill, which is the mixing phase. And typically people throw away this first bit, or try to. But this is just the visual diagnostics so far. More quantitative diagnostics are the convergence tests, which you have to do if you use MCMC. So otherwise you don't know if you already converge. The convergence test can only detect if the chain is unreliable, but it cannot prove that it's reliable. If the convergence test says, okay, it just means detect not okay. One convergence test that is quite easy to understand is the Gelman-Rubik diagnostic, and the idea is the following. You run one MCMC chain, you run another MCMC chain, you run another MCMC chain, and you segment each of those chains into bits, so you chop them up, and then you compare the mean within the chops, within the parts, and the means across the parts. And if your chain explored very well, then those means will be indistinguishable. But if one chain went over this direction, one chain went over that direction, then they haven't converged yet, and it will detect that. So that's basically the idea. But there's a whole bunch of research out there on convergence tests. Do you want to? You have more experience here.
Yeah, I mean, Gelman says don't use Gelman-Rubik anymore.
Yeah.
It's your chain, or it's Gelman and Dan Simpson were two statisticians. They say your chain is never converged. You can, for any non-simple linear Gaussian model, your chain is never converged.
Well, that's not very practical information.
But I mean, just in general, it's if you have a complex model, you have to run a bunch of tests and take it with it.
Yeah. Good. Then I want to briefly mention some examples of global optimization algorithms. Again, this is a very large field of study that many people are looking into.
Just a quick thing, because I think this is an important thing that we have probably not stressed enough. Sorry about that. I think a caveat in all of this is that there is a tendency, I think, in our field, and we'll probably talk about this also when we talk about line detection and things like that, to solely rely on the power of statistical tests. Right? Something is true if it passes every test. What we should not forget is that you will also often realize that you run into things that are not physical. Right? And I have too many fights with referees. For example, I don't need to look for large correlations if I have an emission line that is so strong that I already see it. Often here, what you see is you find correlations that are, and results that make physical sense. And we should, over all of this, not forget that we do physics and that we have this additional knowledge. Otherwise, you could automate everything that we're doing. I think this is an important thing here, right? I mean, these tests are okay, but if your results look, if your statistical tests tell you this is perfect, but if you see that it's obvious bullshit, it is bullshit even if the statistics tell you otherwise. And that's unfortunately a lesson that is not often enough applied.
And the statisticians are screaming this right now. They're
Yeah.
basically saying we don't know how to do this numerically. If you should need to use your domain expertise as well. We can get into that when we get into models.
So it can be fun to do all of these tests because you have the feeling that you really worked hard for the whole week. But from the beginning, it's completely clear that your object cannot be only at 5 AU away from you. All of that statistics won't help you. Okay, and that's, in my experience at least, that's a problem that people often have. Yeah.
But then this shouldn't be in your parameter space.
Exactly.
Yeah, exactly. But right? We like to switch off our brain because there are all of these cool methods.
Perhaps that is an important thing, but it's I mean, the Python thing is very clear. But what if you have something new, which statistically fits everything, and then physically it's a new discovery? So then you get, hey, there are things that are not so easy.
No, I agree with this, but I'm just saying, right? We do the astrophysics, and don't forget that you're doing astrophysics, and you use the tools here. That's what I'm trying to say.
It's not so easy in practice.
Yeah.
And we're
That keeps us in the job.
Yes.
By the way, yeah, you can also learn something about your physical model here, because if it wanders up and down here, what it tells you is this kind of looks similar to here, and you learn something about the structure of your model and how it looks to your current observables. Another thing is if you do best fits, and your best fit lands sometimes here, and sometimes here, and sometimes here, and you plot a line correlation plot between your best fits, right? Some people might think, oh, you discovered something great here, some physical correlation, but actually you're looking at the structure of your model.
Degeneracy.
Yeah, degeneracy, which is also a slang word, which in some other communities is used differently. Non-identification is heard last week. Anyway, global optimization algorithms. Again, huge field. I'll just show one. The idea is that you have multiple solutions which look very similar to your data, and this beautifully hand-drawn graph with multiple maxima, and your best fit might end up here or here, but you also want to know about that one. Or in 2D, you can draw contours of the hill. So how do we go about making sure we explore all of them? Well, there are a couple of general strategies. One strategy is you have your local optimizer, and you start it from a whole bunch of locations. So you draw random starting positions, and you do your local optimization. Another strategy is to make the surface easier. Basically smooth this out or dampen it, and that's called annealing. Also can be combined with MCMC. You start with basically a flat surface, and you take the function and suppress it, and then you loosen up the suppression until you have your real surface. And the flat surface is easier to navigate, so you jump around, and you end up sometimes here and sometimes. Another approach is to have a population of walkers, so a whole bunch of points that jump around and populate the space, and hopefully some will be here and some will be there. And the MC was also implemented in Expect. That is one example of that. So you have a whole bunch of walkers. But again, if all your walkers are here and they learn this distance of very narrow distances here, they will never be there. So again, you have to think about your starting positions. Here I want to mention another algorithm for optimization, which are genetic algorithms. In genetic algorithms, you again have a whole bunch of walkers, so initial population, and this is the first parameter, second parameter, third parameter, fourth parameter. And the idea is that this object, this individual, now we interpret the components, its parameters, as genes. Okay? And so this walker has these genes, and now we make a crossover and mutation step, which is inspired by genetics. So you take two of those. Here's the first one, here's the second one, and you combine their genes. So you take for this one the first parameter of that one, and then the second one, you take them, and so forth. So you kind of combine them. And then you have this combined one. You do another mutation step where you modify each parameter a little bit, twiggle it a little bit. And then what you've done is from your initial population, you have this offspring population, which is kind of a mixture with a little bit of jiggling of the initial population. Okay? But so far, we've just done fun things, but we haven't put in the likelihood or the constraints from our data that we actually want to explore. So now comes the selection step, where we pit this population against that population and let the one survive that did better. So we take the first one and the first one here, and we let them fight, and we evaluate their fitness, which in our case would be the likelihood. And we take the one with the highest fitness, maybe sometimes we let the one with the lower survive, just so we can explore the space a bit better. And then you have your new generation, which contains some of the offspring and some of the initial. And then you repeat this and repeat this. Okay. There are many ways to specify each of those steps. One particular efficient way to specify this crossover mutation step is differential evolution, which is you take actually 3 individuals, and you take the parameter vector between this one and that one, and you add it to that one. So you translate this vector, add it to that one, you make an offspring of that one in this direction. You can vary the length, but that's the idea. And again, similar to Goodman-Weary, the idea is that if your population lies in a very correlated space, then it will preferentially propose in that direction, and less far in the other direction. So it kind of learns about the structure of your problem. And the nice thing is, because of the selection step, where always the farther away points die off, it zooms into the region with the highest fitness function. And that's implemented as Moncar in Sherlock. Advantages of this algorithm is it's a global algorithm, so you can start it with a whole population of walkers everywhere, and it will slowly move towards the peaks. It's robust to degeneracies, it kind of auto-tunes itself. It also works in very high-dimensional spaces, and it even works if your parameters here, because we interpret them as genes, you could even have categorical parameters. It doesn't have to be continuous. Disadvantages are these genetic algorithms have some tuning parameters, and you need to specify when you stop the whole thing, which does not necessarily have a meaning. And it does not provide you with the chain. It doesn't sample. And I will move the global sampling algorithms. That's the 4th category. I'll move it a little bit later to model comparison. And let's take a short break. Yeah, let's take a 5-minute break, and then at 3:30 we have a longer break. Okay. Any question? Oh, yeah. Question.
Maybe you would know a bit later, but then you can actually well, that's why I want to combine unit algorithm with MCMC.
Yeah, people have done this. There's
So
also. Sorry?
I don't think it's so bad. You can always add the advantage of one method with try to not have the disadvantage.
That's essentially what Goodman-Weary is, because it's older and it's younger than this idea. This idea came before. And there are also differential evolution MCMC algorithms that people have tried. The tricky part is MCMC is stronger than just finding the optimum. So you have to also have this condition in there that jumping one way is equally probable as jumping back. And that allows you only to define certain proposals.
Yeah, and but there's another advantage of MCMC and unit algorithms. Basically, you can pairwise the thing. So actually, you can especially unit algorithm, you can really go really fast if you have 500 cores, because you basically have many populations starting at different parameters corner, and then you go to the center.
One of the problems though with any of these algorithms is so MCMC has a theoretically proven mathematical convergence, and these are all heuristic. So you get an answer, but you don't know, you could be infinitely far away from any kind of global, any kind of target distribution.
No, I use MCMC after the unit algorithm.
Right, so when you do that, you break the theoretical proof of MCMC. So it could work, and for very simple problems, but for very complex problems, you will never have any kind of mathematical way to show that it's the true way. That you cannot have everything.
Yeah, 35. So,
Sorry, can I ask a quick question about the fitting methods out here?
yes.
So, is it possible to include upper limits into a fitting method?
Maximum likelihood, no. There's some Bayesian ways. I mean, I haven't never run across a way to do it effectively with maximum likelihood. There's a good paper by Eric Feigelstein, the survival analysis, but that's the only maximum likelihood technique I've ever seen that actually works. Or should work.
We should also say, I think that's another thing we haven't mentioned so far yet. Other constraints are, depending on the method, certain constraints also are difficult to implement or not possible really to consider. For example, formally, Levenberg-Marquardt does not allow parameter boundaries. Even though you always have limits in most of the models that we are using, formally they break the method. And there are similar limitations also to MCMC and so on. So always when you have things at the boundary, you've got to be very careful because you're really screwing up your statistics.
Same with the UX. It does weird transformation of the boundary.
So, but on the other hand, physics has boundaries, right?
The upper limits, I guess that'll go into the SED stuff as well.
Okay, so we're now going to talk about two things which are a little bit out of the originally planned order. The reason for this is that I unfortunately have a stupid private constraint, which means that I have to leave very soon because I have to fly to the US tomorrow morning, and I have to kill a mouse in my house. And sorry. But I think we can fit these 2 points here anyway, are flexible enough. And so what we want to talk about, one is the question about binning and how would you do binning and what is binning. And another question that is related to beyond X-rays, so SED fitting. So we'll be talking about these things a little bit out of order, but sure flexible. So the first thing to talk about is optimal binning. And I will mainly tell you about one paper here that's another of the papers that everybody who's doing X-ray astronomy should have read. And that is a paper by Garching and Planck on optimal binning. If you have been in the field for longer, you will notice that Baker has been dead for a very long time, I think, several years already. This method has been around for a very long time and was never really published, but it's a very important piece of work and part of X-ray analysis, and I would really recommend you that you take a look at this paper as well for the intricacies that I can't talk about. So we come back to the evaluation of our fit function. And so far, wherever we were talking about
about this equation, we never really spoke about where the number of channels that we use, or how to do the discretization of this integral equation to the sum. Right? And it turns out that how to do this is very important. And this is summarized by Wilms. In other words, how many different energy channels should we use when we integrate here over dE? How do we do this in order to make sure that whatever we calculate here as the sum really approximates this thing up here? And also, how many values of this channel here, of the electronic channel, I channel, should we choose? Should we use? Okay? In practice, before this paper, nobody in our field had, ironically, ever really thought about this. People had thought about it, and the answer was more or less, oh, you should probably take enough electronical channels that you oversample the detector resolution. And the rule of thumb there was, you probably should have 3 or 4 or 5 channels per resolution element. In other words, if you have a resolution of 50 electron volts, say, then you should probably have an underlying grid of channels which correspond to about 5 eV in width. Now that was kind of the rule of thumb, but that's, for example, how XMM was built. The same was that, oh, for the number of energies, you should probably be a bit better than the resolution of the instrument as well, and let's perhaps go a little bit higher than this factor 5 to 10. Okay? And both of these statements really are not that well funded in statistics. But first, let's look at how response matrices are really implemented. And if you look at the structure of a response matrix, so this thing here, it fits, you will find they consist of 2 parts. One is called the matrix, and the other part is the E-bounds. The matrix here is really the response matrix. What it tells you here in the columns is there is a low energy and a high energy, and this information down here is one row of this figure that I plotted previously. Okay. So what this tells you is for a photon between the energy low and energy high, this information here gives the probability that you end up in a certain channel. And as you can see here, for example, for in this case, this is the timing mode of the epic PN. Somebody decided that one should use 2067 of these channels. I don't know who somebody was. Konrad, was this you?
No, not me.
And so, right, 2067 times 5 makes 10,000, and right, XMM uses about 5 bits. On the other hand, somebody decided that each PI channel should also, well, have a certain width, and the E-bounds column tells this to you, and there it was decided that there are 4,096 of those. Which kind of makes you wonder that somebody was thinking, well, 10, 10, 24 is probably not enough, so let's add a few more bits on top of it and end up with that number. Okay? Both is not really a scientific approach. Right? So in other words, how many bits should we have here, and how many bits should we have along this axis? That's what we're trying to answer. And from your point of view, of the interest is, you should have enough bins in both directions that you can recover all the signs that's possible with the instrument. Okay? Makes sense? But you shouldn't have that many more. And the reason for this is just that we were talking a lot about function evaluations, and you see that your MCMC is running around, and each time that you're doing this, you're performing these really complicated sums. So if you have a response matrix that's completely oversampling what you should do, you're just heating the building because you're computing a lot, but you're not adding physics. And your fit might not take only one day, but a full week before it converges, okay, with the same result. So this is the question of how should I bin in order to get all of the signs out while minimizing these numbers. And the answer is given in this paper by Kastner and Blaker. And it really starts with the number of energy channels. So let's ignore for the moment the effective area, and let's assume that we just have a simple response matrix. The idea that I have then is, okay, how do we write down the discretization? Well, we write it down in this equation down here, which is this. And then let's think about how do we evaluate this flux here that enters in this sum. Most analysis packages will very naively just say, let's choose some energy in this bin, which goes from E1 to E2. For example, let's use the middle, or let's use the lower value, or let's use the upper value. And let's multiply with the width of the bin, and this is the value to enter here. Okay? So this implies roughly constant over the delta E. And in other words, this says use a sufficiently large number of bins such that you can describe things. I mentioned before, XMM decided 5 EV is enough, Suzaku decided 1 EV is what one should use. Out comes 10,000 bins roughly in the matrix, which on a good computer you can use, and you can do work with. But let's really think about what sufficiently large means in terms of a science. There's a rule of thumb that you can also derive using simple Gaussian statistics on how well you can determine a line centroid for a delta function line emission line. Okay? That's a typical astrophysical question. And the answer is you can measure the line to an accuracy that's about resolution divided by the square root of the number of photons in that line. Okay? So, what does this imply for the bin number? Let's assume we have an instrument like Athena W of I built here in the house. We'll have a resolution of 1 keV that is approximately 20 electron volts. Let's take an OK star with an emission line that has 20,000 counts. Something that's a tenth of Capella will do this in a few kiloseconds with Athena. Okay? With this, you can measure the location of a narrow line with W of I to 0.1 eV, so much better than the resolution of the instrument. And this means if you want to now evaluate your response matrix, you want to let your algorithm know where to put this line on the energy grid. Okay? If you do the minimization, you move your line value around, and so you need to describe your energies with a resolution that is about this value. And suddenly, rather than having 10,000, we have 100,000 bits in here. Still okay because the launch will be 2032, so computers will be faster, Moore's law will help us. Fine. However, there's also the Athena XIFU, which will cause a bit of a problem because this is a 1 eV resolution and you have 2 million bits here. And you will have brighter sources, so you will be even better with your measurements. And that means just throwing more bins at the problem is not a good idea. You need to think more about how to do your bin. Okay? So, already now, if you fit more than simple absorbed power loss, we are at the limit of what our computers can do. I'm working with models that require 5 to 10 minutes per evaluation of the model. Okay, that's why I was always asking about how many model evaluations we have. Right? Now, I'm lucky because I work with galactic sources and they are bright now, but the problem is if you have a much larger effective area like Athena, many of you who said, oh, I look at AGN, will suddenly have data that have a signal to noise that's high enough that you cannot cheat and just fit a power loss with an iron line. Okay? So everybody here will have the problem, unless you go to redshifts of a few. Right, that's my theory why people like to go to extragalactic. You just increase your set in order to keep the signal to noise of your data small enough that you don't have to worry about these methods. Anyway, so this is the problem. So if we go back to what we just did, what we effectively said was we put all of the line and the delta function in the bin, and we just chose the middle of the bin, and we said in the evaluation of the F, that's what we do. And what Kastner and Levenberg do in their paper is they look at the higher moments on how you can calculate the integral to approach the proper the proper integral. And well, obviously you use integral theory, so you go to higher moments of your function. And the next thing is, for example, rather than evaluating the middle of the bin, look at what is the average number of photons that you have distributed over your bin and use the average. So do this. Or estimate, for example, for your evaluation, consider also that you might have a complex shape with higher moments and evaluate the function then. Okay, so you evaluate the average energy once, then you know where to evaluate your model in the spin, and use that value rather than the middle. Okay, so for example, if you have a line that is in your bin, do not evaluate the value of the line in the middle of the bin, but where the line is really located. This is what I'm trying to say here. Okay. So, now if you know this, so if you know where the EAs are, you can then place your grid such that you can always choose an optimal evaluation of the function. That will depend on other parameters of your instrument. For example, it will depend on the effective area. Okay? We've seen that the effective area looks like this. So you probably want to put more bins where the effective area is changing quickly, because there you know that the average area will move around a lot because you have a steep gradient. While in flat parts, you can describe your model with the shape of what you're doing with less data points. Okay? And now the question is, how do I distribute these points around such that I get a specific number of counts per resolution elements? And choosing the middle way, which is what we are using nowadays in our data analysis, what I'm plotting here now is the number of counts per resolution element as a function of, and the bin width per resolution that you want. Right? And what you see here is that the number of counts per resolution element, if you want, say, 10 to the 8, you already need to go to 10 to the minus 4 bins per full width half max. So you need to put 10,000 energies in one resolution element in order to describe the spectrum to the desired order. Okay? Which is a lot. Okay, and that's why evaluating Suzaku spectra takes so long. If you choose the energies in a more intelligent way using the average energy, you get this red color here. And you see that even if you want to say an overbinning where you have about 100 counts or so per resolution element, choosing your binning such that it follows that you use this information leads to the red line. Equations for what you use are in the Kastner paper. So this tells you effectively that you can gain almost an order of magnitude in terms of the number of channels. So lose that, and that means that your calculation is faster by this order okay? Which adds up if you use 10,000 evaluations if you do your MCMC. Okay, that's the difference between doing it in a day and doing it in a week. Okay, that's why this is so important.
So this is the number of energy channels, and for the implementation, you need to worry about this if you have to build a response. There are some simple equations you can use. If you have responses that don't do this, there is a tool in the F-tools, which is not that well known, but which is called FTRB and MRMF. Okay, which is essentially a name you should never call your software like this. But this is just rebin the response matrix, and FT means it uses a better way than the old Fortran way. And you can build bin files for this to essentially bin your response matrices such that they approach this, and this will speed up your work by a factor of a few. Okay? And it will work because this is an optimum way. It will work better than just saying I rebin everything to the same energy resolution, which you should not do, right? Because your energy resolution changes. The other thing that you should look at is the number of spectral channels. And the number of spectral channels is important because if you take your spectrum, you bin your data together, you're losing resolution. Okay? If you bin your data, you take multiple of these channels, throw all photons together into one channel, you're effectively losing energy resolution. The question is, how should you bin such that you're losing the least of the energy information, have the lowest number of bins total? Okay? So bin enough, but not more than enough. And the answer to this is effectively given by information theory. And if you have a so-called band-limited function, a thing whose Fourier transform is 0 outside of a certain band, which is the case for most physically okay functions. Shannon showed that you can describe a function f of x by this weird sum here. The important thing of this sum here is that what this tells you is that you have to evaluate your function only at equidistant points in space in order to describe the full function. Okay? So using the information theorem, you can derive really easily derive what bins you should use and evaluate your function. Since we're having to deal with bin integrated quantities, you really need to take this thingy and integrate it, which causes a very ugly function here. And then you need to invert this to get the energy resolution. And the nice thing of this is that using Monte Carlo simulations, one can show, and again, how this is shown in Castle and Laker, that if you choose your delta per resolution element according to this function here, in which you have to plug in on how many photons do I want per resolution element, and you just set the n to 1, and for the resolution, well, you know what your resolution is, so you can derive this. You can derive how you should bin your channels. Okay? So with this, you can calculate at what energies you want to evaluate your function in order not to lose any physics. Okay? If you bin more, you're not going to win in terms of information. That's what Shannon tells you. Okay? You might naively think that by binning more, you can prepare out, for example, certain structures that you see in your data. This is true because you as humans are not good at doing statistics in your parallel computer up here. Okay? You should bin more in order to get intuition about what your spectrum looks like. But don't forget that the analysis is done by algorithms. Okay? And they will find better solutions in the data, even though they are hidden for you, because they don't care about the big peaks. They care about, oh my God, there's a line, so I do have a deviation from the continuum. Okay?
So what you should do is you should effectively win according to this equation and not more than that. That guarantees that all of the data, that all of the information that is in the data still is in the data. And for the rest, then the model algorithms are what you have to do. Okay? So what we do traditionally is wrong unless you use specs. Because that was written by Castra and it has been built in like that. And if you choose this approach here, you can approximate in terms of speed and so on, also with other pieces of software without losing physics. Okay? That's it about binning. There's a third thing which I'm not mentioning here, but in principle, you can do even more optimization by looking at the shape of the response matrix and, for example, building various response matrices with different unique energy grids, which you then merge, for example, to separate out narrow line cores in the response matrix and, for example, Compton continua. And if you mix these things, you can find an optimum way on how to evaluate the model function such that no information is lost and that you're asking the computer to do the least amount of work. Okay? That's what binning is about. Note, I have not spoken about throwing in more things than necessary. And the reason for this, again, is that overbinning will not help you in your analysis. It will only make you lose information that is in your data. So don't do it. Okay. Questions? Okay. Then we do another don't do.
Before going on to model comparison and some more hardcore statistics, we can talk about one thing, plotting, and another thing, what our data actually are. I would come at this. So we're going to talk about SED fitting and the analysis of SEDs, both multi-wavelength and just in individual instruments. And then I'm going to give an example from a field that probably most of you are in gamma reverse that most of you aren't aware of, but because of the broadband pass of GBM, you can really see how if you try to do SED fitting in the wrong space, then you'll get the wrong answers about what's going on in physics. So you've probably seen plots like this if you do AGN. I don't. But you see these models that go through here, and then maybe I should use and then you see these data points here. But these units, of course, there are no instruments that measure flux, maybe optical. So where do these data points come from? Right, and they're from different instruments. I mean, here this is, I guess, this TXS event where you see some neutrinos, upper limits like you were asking about earlier. So what's happened is that these are observations from different instruments. They are measured maybe in counts or however IceCube measures light in these optical domes. They're fitted with a model, usually power laws. And then people take and turn those power laws back into new data points and then fit them again with a model that has nothing to do with the original model. And as Joern's been going over for some time, these instruments have nonlinear responses. So going from the shape of the model that you choose, when you do this convolution, has a big impact on these shapes here. For small band passes, it probably doesn't matter. For optical instruments, when you're looking at little bitty things, it probably doesn't matter that much. But when you start looking at broadband spectra and across instruments, these things start to matter. If you deconvolve, when I say deconvolve, I mean you fit in the native data space the instrument fit a power law that doesn't have anything to do with that between the two instruments, the answer you're going to get is nonsense. And it's not going to allow you to do any kind of detailed physics.
If I may briefly interrupt here. How many here have looked and expect that something at the output of plot UF spec? Have you looked at the output of only 3? You've not looked at plot UF spec? Do you know what you're seeing when you do plot UF spec? What are you seeing?
You basically see transposition in the bottom flat space of your data, but through your model.
No.
No.
Okay, what we're doing is what expect does to do plot UF spec is it takes your current evaluated model, and for each channel, it looks at the ratio between the model that is folded through the response matrix and the measured data. And then it multiplies the value of the model in the middle of this bin with this ratio. Which means the flux that it is plotting depends on your assumed model. Okay, so it's not looking at all at what happens to the photons. It compares apples and oranges. So the same spectrum will result in various different unfolded areas. That's why you should never do plot UF spec.
In fact, yeah, so let's go back through real quick on what's going on when we do a spectral fit. Okay, this is our data. Right, and this is the model that we want to fit to that data. And when we do that, we have to fold through this response. So this is GBM, so it's a much broader. It's got a pretty wide bandpass, but in order to move this model into the count space where we actually want to do the fitting, we have to fold through the response matrix. So you know what I'm going over this. And the reason is that models can look very, very similar in count space compared to how they look in new space. So these will result in basically nearly the same fit statistic, but they'll be slightly different models. Now, it seems like this is not a big deal, but the problem is when people are doing these multi-wavelength SED analysis, and in GBM as well, people try to do physics with empirical models that have been fit to the data, where they look very similar in count space, but they look very different in new space. And I'll just give you an example of where this kind of starts to break down. So we typically, in GRBs, we want to try to fit different numerical spectra. We want to fit synchrotron spectra. And this is what synchrotron spectra look like. However, to do this, we have to compute a very difficult numerical model. We have to solve a continuity equation. And this can be very expensive. Now, to get around that, instead we try to fit an empirical function. We call it a band function. You can think of it as a smoothly broken power law. And an interesting thing about synchrotron is that depending on how cool the electrons are, how long they've been radiating in the magnetic field, this low energy slope of the synchrotron spectrum will change. And so people say, okay, well, if I can fit this smoothly broken power law to the data, go back and look at what the index of that smoothly broken power law is, I can compute how cool the electrons are in the spectrum. And so people go and they look at catalogs. They fit a bunch of spectra, and they look at catalogs of these low energy indices. And then they try to do physics from this space here, instead of in the count space. Okay, so if this allows them to determine whether or not they're looking at the photospheric emission, synchrotron emission, and different cooling regimes. However, we found that you could actually, if you want to go through and spend the time to compute this numerical model, you can actually fit synchrotron to a lot of these spectra in the count space when you actually fold the model through. That would have been rejected if the index would have been too far to one side or the other of this alpha distribution.
So people said, okay, maybe this is how it works. So instead, what we'll do is we'll try, instead of measuring the low energy index on this empirical function, we'll measure the width. And they came up with different measures for how to measure the width. They can do the full width half max. They can look at maybe the angle that this function does. But they do this in new space. So in other words, they fit this empirical function, this band function, then they go back and they look at the shape of the band function in new space from the fit, the result of the fit. And the idea was if it's very wide, then perhaps the emission could be synchrotron. If it's very narrow, it looks sort of like a black body in new space. I'm just going to... Okay. But, and it basically ruled out synchrotron emission. I decided to test this because I figured, okay, maybe what's going on in new space is not really what's going on in the count data. And so these are two spectra in GBM. In the count space, not the new space, we went and fit synchrotron, where synchrotron should have been ruled out by doing this empirical analysis in new space. And what was interesting is you found that, yes, there were some spectra that were allowed to be fit by synchrotron. If this circle ends up in this gray box, then it should be, synchrotron should be rejected. But a lot of spectra were able to be fit in this rejected region. And in fact, these two spectra, which are fit to synchrotron, which should strongly be rejected, ended up being quite good fits to the data. And this comes back down to where we need to evaluate our models. That these functions look very similar in count space, but they're very different in new space. So if you're doing analysis here, instead of fitting by folding through the actual function you want to test, you're going to get the wrong answer. And just as one more example of why this is going on. So those two fits that I showed you, if you fit this band function, this red thing, to the data, it will come out as this shape. If you fit synchrotron to the data, it will come out as this shape. Same thing over here. And it's because both of these are very good fits to the data, but because of the energy dispersion in the response matrix, you can't really decipher between them. So you can't use things that are going on in new space and model space to infer physics. And so, I guess Joern will probably agree, if you want to do multi-wavelength analysis or any type of analysis where you want to test some physics from an empirical function fit, you need to do it in the native data space of the instrument. And the way that you do this is by summing together the likelihoods from the different instruments, where the likelihood is evaluated in count space. The model, the physical model, is folded through the response. And this is really the only way that you should be doing multi-wavelength analysis, not doing this in these deep involved new spaces, because you will get the wrong physical things. You want to add something to this.
Yeah, so what was just shown was for high energy data, but the same thing applies also to, for example, combining optical infrared radio data with X-ray data. About 95% in the literature of SEDs does deal with new fits. For example, there's a whole industry out there in the area of laser science, where you really have to fit from the megahertz to the MeV block. And most of the theoretical results that are done there are unfortunately done using UFO fits like this. The reason for this is there are also fits by eye, by the way, because the models are fairly complicated. They might take hours or days to converge. But a lot of the conclusions that were drawn in these fields are probably affected by data analysis issues. Just to give you a few examples what to be careful of. If you take values from the Fermi catalog, flux values from the Fermi catalog, which is often done, they are based on power law fits to the Fermi band. But laser spectra look like parabolas, they are not power laws. The reason why a power law describes the data is just that the signal to noise is so bad that you really can't distinguish the models when you're just using this data band. But the resulting fluxes that you infer are very different. Another example is de-reddening optical data. Okay? The thing that is done in optical astronomy and that optical astronomers can do with very good success is by measuring, when you measure magnitudes, which is a fairly small band, what you're going to have is there's dust between, and you have dust between us and the source. We know what the extinction is as a function of wavelength, and de-reddening means nothing more than assuming a column of stuff between us and the source, which, by the way, is often derived using a relation by Dennerl that has been revised 3 times since then, but people usually still use the Dennerl X-ray determination for the dust ratio, and then they measure the column and then adapt the magnitude to the de-reddened value. This is fine if you look just at small narrow bands, and with some empirical work you can usually get an okay description of the fluxes there, but you find that often these values that one gets out of the de-reddening, for example, disagree with values for the column that are measured in the X-rays. The X-rays measure the total column of material, and if you use dust models, you find that there are strong deviations for the dust value, so that you can't use the Dennerl for many lengths of time. So if you do this, and for example have joint optical and X-ray data, you can always go and really use a proper dust model that uses proper columns, and really using exactly the same description as that we have here to really model your optical data. Okay? The answer there is don't use magnitudes, but use effectively a photon flux, which you can derive. You can also build up response matrices. In the optical, they are very simple, because essentially it's a Gaussian. The effective area that we're talking about is nothing more than your filter function, right? The UVB and so on filter is nothing more than use a specific effective area. And this way you can do joint fits over broad bands. In principle, you can do this in X-ray. You can also do this in ISIS very easily. We have written, for example, functions with which you can do that. And then you stay in this native data set, and effectively you do not have to worry about applying empirical linear correction factors to your measured data, because you can do exactly this. Nothing is stopping you from this. Right? The reason why this is not done is that traditions in different fields in astronomy are different. Okay? And so people apply different data models and different terminology, and that leads to us in the field overlooking the commonality of the data analysis approach. Okay? So functions for reddening, for example, are available, so that in principle for most of the SED work that you, if you come from X-ray astronomy, will have to deal with, you can probably really use your own tools. And just because your data were measured at a few thousand angstroms rather than at a few angstroms does not mean that the data won't break stuff.
Different a bit SED fitting. Although I don't fit the high energy part, is that I think it's just a question of vocabulary. When people fit the SED without the high energy part, so like optical to radio, the nu F nu is actually the data. It's just that we don't put count. We still forward the response function of the system. So when you say should not fit F nu, you should say in the model F nu, not in the observational F nu, because whatever we do, we still don't nu F nu.
Right. Yeah. it's called, I say new space, but it's in the model space. You shouldn't fit deep involved spectra, especially with the different.
Yes. Yes. Yeah, it's just a vocabulary, but don't say we should not fit in nu and nu, because in other wavelength it's nu and nu.
But you should not fit in flux space, in other words, because nobody in astronomy is fitting fluxes.
You have to use fluxes, rather than manipulate.
Yeah, but in optical astronomy you're also not measuring fluxes.
Agree, but still better than nothing.
Yes.
We can, but I think this is the graph.
Actually, it's just a way to plot. You can just say f nu and you divide by nu and then you have the same thing.
Yeah, but this value is as wrong as the nu again.
No, the value is correct. It's
No.
No, it's still correct.
At some point, somebody that might have been like Planck
Yes.
proposed some better way of turning your, basically producing a flux spectrum than using unfolding. It is.
Okay, the second author on that paper, or the last author, but one of the other person who proposed it was me.
Okay, but does that work? Is it valid? As an author of the paper. You just said it isn't.
Part of the calculation is less shitty. Because it is not model dependent.
And how does it work?
Okay. Okay. If you want to plot fluxes, at least in a way that is reproducibly wrong, rather than depending on your what you do in XVEC is okay. So in principle, we are saying
This is the equation that we were looking at. Read my handwriting. Sorry, I'm an intended person, which means I never. Yeah. So you say this is approximately f of e times the integral of a times r times dE, which is approximately f of e times a effective and r times delta e, because the r integrates out to unity. So the conclusion is that for a detector that only has a diagonal response matrix, f of e is approximately n divided by the effective area times the bandwidth. The way to do this, if you use XVEC, is you say model power. It will hurt you because you don't have WAS before that. So you just say model power, set the photon index to a constant, and then the machinery in XVEC will, if you do a plot to XVEC, will give this. This is still wrong because of all of the side terms in the response matrix. But it is the closest approximation to an inversion of the of this equation that it can do. Yeah? But for plotting, this is okay. For then fitting something through these points, this is not okay. Because the leakage terms in your response matrix, as soon as the response matrix isn't just a narrow Gaussian along the diagonal, you can make a large mistake here. And that's effectively what we're saying with don't fit mu with mu or f.
So if you do plot unfold in ISIS, for instance, then it assumes
that regime was written by Mike.
Then it
exactly this.
It assumes a diagonal response matrix.
You effectively assume a diagonal response matrix, and you assume that all of the leakage into other channels and so on is not there, and you assume, for example, that the channel energy that you have in that you have to use to calculate this delta E here is okay. Okay. The way how the channel energy is derived, if you look at the response matrix, is you essentially look at what is the peak right? We've seen the figure. You look at what is the peak channel in which most photons for a certain energy will end up with. Okay, that's how you map energy into channels. And then you essentially chop this into something that's equidistant. But the whole channel energy, nowhere in what we said today did we use these channel energies for anything. The only place where they're used is, for example, here, or when you also do UF spec in X spec.
I actually hate that they put channel energies because it's reconstructed energies.
Yes.
And this leads people to think.
Small story about this. When XCE was launched, 99, okay, last millennium, the Hexty response matrix was built by Buchner. And Buchner made a small mistake in two channels in Hexty, where the energy being in the channels was not equidistant enough. And when you did the plot of UF spec in X spec, you suddenly saw that the counts changed a lot. So when you plotted a UF spec, suddenly your unfolded spectrum would have a jump there. And people started complaining about absorption edges in the data for everything. And this had just to do with assigning not a wrong value to this channel, because the channel energy does not exist. It's not a quantity in the whole data model, but just because people were taking these values serious.
I mean, so when you do things like hardness ratios in count space, and you say, oh, I do a ratio between 50 and 300 kV or something, this is meaningless. Because, especially for an instrument like GBM, most of the counts at low energy come from much higher energies, like physical energies, because there's a large amount of dispersion. So this leads to weird quantities that don't really have much to do with physics, that people try to do physics with. So say, if you want to do things like hardness ratios, you need to fit a spectrum to the data, then you can go back into the model space, and then you can do some analysis there. By computing a hardness ratio, by integrating over the flux model. But of course, that's going to be model dependent, whatever you actually fit to the data in the first place. Unfortunately, you can't invert this matrix. And that's what all of these things are trying to do.
In other words, I'm still worried. I've said this a few times already, right? With Zeta, we might be providing something like fluxes to people. Right? This has always been discussed. Should there be fluxes in Zeta catalogs? And it is mathematically not possible to provide fluxes in the Zeta catalog.
Well, yes, but the response is fairly bad.
Exactly, that's then the answer, right? So I understand that whole discussion. It will be interesting to see when we get the first message where people misinterpret what we're showing them. Because obviously it makes sense to get a feeling for what's going on. The danger is when people take then these points and do the big broadband work.
I'm not sure if you said this already, but how do you treat, or how does one have to treat then the instruments that need an input model for calculating a spectrum?
So the way that, this was, I guess, why we wrote 3ML, is that you have to use it. So for an instrument, I was going to give another example, Fermi Lab.
Yeah.
Right? It has a very specialized likelihood model. And funny enough, Fermi didn't provide software that allows you to fit GBM and Fermi data together, or lab data together. So the reason is because the likelihood model for the lab is incredibly different from this type of data. So what you have to do is fold that model through the Fermi software while you're simultaneously folding it through this response matrix. And so that's what I mean with the last equation there, is that you have to just treat each likelihood differently. The same thing goes for IceQ, right? IceQ has a huge amount of Fermi dispersion. And people take because IceQ makes the huge mistake of releasing data points, which they don't have, right? They're a hugely background-dominated instrument. They have to make a lot of assumptions to pull those things out. And so they release those data points and people refit them with all kinds of different models. And it's nonsense, because they've already assumed a power law spectrum to pull that data out. And what happens is, I mean, the reason that we wrote 3ML to be able to do that is because we wanted to find cutoffs at high energy in gamma reverse in the lab. But what people would do is they take the lab data, as you said, they fit it with a power law, okay, so no cutoff. They'd fit that with a power law, and then they would compute flux points that you could throw it back into XPath, so not real things, and then they would go fit and they'd find a cutoff at high energy. And the reason was is because you had already assumed that there was a power law, and so you put a lot of statistical power at high energy, and we said, okay, we can't do that. We should, if we want to fit a cutoff power law at high energy and to low energy, because yeah, the idea was we wanted to fit with GBM and Fermi. We have to fold through, and as soon as we do that, well, cutoffs. Okay. So you have to fit in the native data space. Fitting decoupled spectral will physically lead you to a wrong answer. And instrument teams should be really careful about how they release the data. That's why, as far as I'm concerned, like IceCube doesn't exist because they don't actually release their data. Right? It's not public, so you can only fit the Deacon ball spectra, which means that I can't do any further analysis on that.
So the plot you showed before with the two models, could you bring that up again?
Yeah, not the one that I made.
Not this one.
Yes.
No, I think before.
You're probably thinking of this. Which,
No. Was there another one?
No. This.
No, sorry.
Before.
Yeah, this.
Yes.
No.
I don't have any more.
You had one where you
You
had
should learn to make numbers on the slides so that it's easier to go back to
you
what
had
you
one where you had the data and then the two models on the top, both on the right. Yeah, this one. So if one did something similar to UF and projected those data points out, the data points would look different for the red curve than for the blue curve.
If you use the X-spec unfolding, the answer is yes. If you use this unfolding, right, this is model independent, that's why it's preferable. Yeah. So, right, I mean, Paul is right in that if you have a narrow response, if you don't have much leakage in other bands, these approximations are not too bad.
Yeah, but the idea is this is done for the flux and
the RGS fluxing is okay, however, fitting fluxed RGS vector again is something nobody will do, right? And there's a reason, because the line split function is so wide that you can't do that. But what we are essentially trying to point out is that this is a problem for all data sets. Okay, this is also a problem, for example, when you plot UV and V broadband magnitudes, right? You use the SDSF web page to convert this into a flux, and then you plot a cross there, right? That's bold. Not on you, but bold. Yeah.
Yeah, I guess you don't have to do this anymore. I mean, there was historical reasons for that. Is that software is pretty fast, and it exists, and most instrument teams make a great deal of effort to release the response matrices and to do these things. It's an easily overcome problem.
But ESO does a really good job with the fluxes, for example. Right? But people will still go through all of this weird thing because it's been done like that, and that's just.
So is that not implemented next time? This one, this
Well, it's not implemented, but as I said, just do power law for minimizing to all your yeah. Which will hurt you, right? Because there are things you don't do, but for this you do it.
Yeah. Let's make a coffee break until 4 and send Joern off to this meeting. Now we are hopefully slowing discuss more. We have to rush to get Joern finished. Now we're coming to the topic of model comparison. And the idea is, well, so we discussed a lot how to constrain parameters, for example, with MCMC or finding best fit. But that is within the context of one particular model. And often we have multiple competing models and we want to discriminate between those. And that's all summarized under the topic of model comparison. One specific subcase is where one model encapsulates another model. So you have one model and you add a component or something like that. So you have you're extending some model family. And that Michael will talk about now. Switch over.
Okay. So how many of you are familiar with Wilks' theorem? Okay. How many of you are familiar with likelihood ratio tests? Okay, cool. So, a lot of times, as Johannes said, we want to compare two models. One thing with all statistical tests, in general, but especially for Wilks' theorem, we have to remember is that Wilks' theorem was derived in the 30s, and most of the tools and simple checks and tests that we have in the maximum likelihood framework, which I don't like to use, but Johannes wants me to talk about, were derived for linear models. So every time you see things like limits of fit, significance for model components and everything like this, it was worked out. A lot of people did a lot of hard work to figure out how all these simple checks work for very simple models. And nothing has been proven, and these are exact proofs. Nothing has been proven beyond that. So in X-ray astronomy, where we have nonlinear models, Poisson data, and stuff like that, there are things that we can try, but none of them are proven to work. And so they're very fragile, and you have to understand the assumptions that go behind these theorems when you apply them. So we'll start out with Wilks' theorem, and I tried to visually show, what a composite model is. You can imagine that the red and green squares are components of a model that can take on different values. But what Wilk said is that you can have a composite hypothesis and a simple hypothesis. We sometimes call this a nested model, right? So that means that this simple model is a very special case of the composite model. In this case, this theta 3 would be set to 0. And this is the only situation in which you can use likelihood ratio test, period. If you try to compare two models where one is not a special case of the other, the likelihood ratio test will fail. You can get a value, but it would be meaningless. So we should go through the derivation of what Wilks tried to do. So he said we assume, and you have to understand this happened a long time ago, so they didn't really have the concept of a lot of the things that we use in statistics today. We assume we have a distribution function f, and it forms some kind of distance measure between data and parameters. So f can be anything. It doesn't necessarily have to be a Gaussian likelihood or Poisson likelihood or binomial likelihood. It just has to be a distribution that measures the distance between data and model. And then you can form a probability distribution over the data by taking the product for the different data sets. And you let this be this composite hypothesis, so this is the more complex model, and this be a simple hypothesis. And you form this thing, and it's called the likelihood ratio test. And we say that this hypothesis is true if it generates some data set, some observations, ON, so N observations from a population. Now there's a very important clause in this that seems subtle, but it's vital to what likelihood ratio test means. It says that H is said to be true. It means the models that you're testing, one of those special cases that generates the data. And this is, they didn't really call it this back then, but now it's something called enclosed, which means that out of all the models that you're testing, one of them is the true model. In general, in physics, we're never in this situation. So you may fit a nice thermal Bremsstrahlung spectrum to your data, but it's an approximation to what's going on. And if you get enough realizations of the data, you'll find that you'll be infinitely far away from the true, from the model that you're testing, because you don't actually have the true model. So this is one of the fragilities of the likelihood ratio test, is that if you aren't testing something like, are there more boys than girls in the class, which is an enclosed problem, right? One of those answers is true in the problems that you're testing. If you're not using that, then the likelihood ratio test doesn't apply, because it's outside of the assumptions that were used to derive the likelihood ratio test. Now, Wilks set up the problem like this. It's a 2-page paper, and I think everyone should read this that's doing any kind of data analysis. I just want to show this is the original paper back in 1934, and how he set up all of these regularity conditions already in the paper. So when people have discovered that the likelihood ratio test breaks for different kind of conditions, it was kind of already known in the assumptions. But there's one specific one that's really important. So while the likelihood ratio test can allow you to use any likelihood, so in this P little omega and P big omega, you can use a Poisson likelihood, you can use a Gaussian likelihood. The point of this was for him to show that all likelihood ratio tests go to the same thing. It makes a very explicit assumption about how the posterior, well, we call this posterior, but how the covariance matrix, the shape of the error distribution looks. He said it's a Gaussian, so it's a symmetric. And this is always a fundamental assumption in maximum likelihood estimates, but this equation 3 explicitly states that if you do not, if your error regions on your parameters are not symmetric and basically not Gaussian, this stuff doesn't apply. So if you have a bounded parameter, which we'll get to later, or if you find that your errors are asymmetric, then you cannot use the likelihood ratio test to see if one model is better than the other. So he works through all this, and there's some other, if you go through the math, it's just some linear algebra, but to make things nicer, he does a couple of things like assume that the model that you're looking at is linear, because that's all people were curious about testing at the time. So if you're using a nonlinear function, this also doesn't apply. And that's mainly because he found that when you go through all this mathematics, the likelihood ratio test should be distributed as a chi² up to order 1 over square root of n. Now, you can imagine if you have a nonlinear model, where n is the number of data points, the number of data points and the power that you have in your thing can drop off very, very fast. And that's why the linearity really holds to how fast this converges asymptotically. But this is the whole point, is that if I have one model, a complex model compared to a simple model, take the likelihood ratio test, and -2 log likelihood should be chi² distributed. So that allows you to test the models and go off to a chi² table and read off the significance of probability value of how good one model is to the next. And then at the end of the paper, you kind of summarize it really nicely, and it's really worth just saying. It says, a population with varied x is distributed according to the probability function, or likelihood, such that the optimum estimates theta sub I of the theta sub I exists, which are distributed in large samples according to 3. So they have to be a symmetric function, or a symmetric distribution like a Gaussian. And when the hypothesis H is true, that theta sub I equals the special case for all the data, all the parameters, this distribution is given by a chi² up to order 1 over n squared. And again, this is an asymptotic thing. We never really know when we hit this asymptotic value, but it's fine. With h minus m degrees of freedom. So this means that I can go and read how significant the more complex model is, or the penalty for adding on an extra. And like I just said, we want to do this so that we can read off the significance of adding an extra component. And we can test this. So here I've generated some synthetic data.
So, sorry.
Yeah.
So for nonlinear models, it converges faster or slower?
Probably slower. I mean, that's the thing. Which we'll get to is you always have to go and check. The more important thing is that you have to really make sure you're in this regime where you're that it's a nested model, and that the covariance is going to be actually something. So you can check the asymptotics, which is what we're about to do.
But for nonlinear models, it might not converge to a chi² distribution in the first place. So it might be distributed completely different. Exactly. We might not be able to use this at all. And you probably won't.
Yeah. So here I've generated some synthetic data from a second-order polynomial, and you can see the slight bit of curvature here. I've given it heteroscedastic error, so the errors are different along each data point. And the true model is shown there with red. So that's the model that I used to simulate data. And then we can use, I use just an optimization algorithm. And I fit both a straight line to the data and also the actual model, second order polynomial. You can see the straight line, it goes through the data points. I don't like to plot error bars for Bayesian. And then the green line is the fit to the second order polynomial. You see it works quite well. But the question is how I can go and I can compute what my likelihood ratio is between these two different things, and I get that this is about 13.7, or the chi², 10 to the minus 4. Okay. To test this, we can profile the likelihood. And so what I want to do is generate new data sets from the best fit of the simple model, right? The simple hypothesis. I generate new data sets using those best fit parameters from the likelihood. So in this case, it was a Gaussian. I create a whole bunch of new data sets from the simple model, and I fit each of those data sets with both the complex hypothesis or composite hypothesis and the simple hypothesis, and I compute the likelihood ratio with each one of those fits. And then I can histogram that. So there's the -2 likelihoods. I did 100,000 simulations here and just normalize. And then I can plot over the chi², and you see that it's actually distributed like a chi². And I can go off, there's just, because I haven't simulated, I should actually do 10 to the 5, but I don't have time. You can see the reference statistic where it lies on the chi² value, and it's about equal to what the histogram was. So under the ideal conditions, one of the models that I've tested is actually the true model. It's an actual nested model. It's a Gaussian likelihood. Everything works out. But this is not going to be the general case. So here is a simulated spectrum that I folded through the GBM response matrix. And what I've simulated here is, and this is in count space, it's a cutoff power law, and blue is just a power law background under that. And I want to test and see if I can find a cutoff. So I will fit by folding through the response matrix using the appropriate Poisson likelihood. I'll see if I can measure this cutoff in the data and see how significant it is. If I run through the machinery that I just showed you to test Wilks' theorem, and then so that's all these blue things here. There's my reference test statistic, or -2 log likelihood. And I overplot this chi², we see that it's not correct. It's off. And it's actually off by about a factor of 0.5 multiplied by chi². This is actually a well-known result. In fact, some people from here looked at this a long time ago in egret data. And you typically, for Poisson data, when you're fitting power laws, you'll see that it's off by this factor of 0.5. I still wouldn't use that as a golden rule. You should always profile your likelihood ratio. But even strange nonlinear things can happen. This happened in egret, where it looks really nice. You can simulate up to a certain number of values, but then at higher values, this thing can even uptick sometimes. And we found this in GBM data when you're later about fitting multiple components. So the point is that the likelihood ratio test is very, very specific and has a lot of regularity conditions to it. And you should never, ever just do, oh, I have a delta log C stat, or C stat, delta log, delta C stat, delta Poisson, delta chi² even most of the time, and use that to say that my model is better, unless you've gone and profiled a statistic. Because it's likely not distributed like a chi². If you do non-nested models, you'll find something really funny here is that this will actually go negative sometimes, which just means that the likelihood ratio test is breaking down and it fails. So you can't use likelihood ratio test for non-nested models. And nested, while it seems like a very simple concept, just a special case of the model, there are other regularity conditions that we'll get to with Burgess that indicate what's going on with nestedness. So you typically need to do what Johannes is about to talk about to deal with those types of models. In general, you should use Bayesian model comparison. So are there any questions?
What do you consider as a simple model and what is a composite model? Is
So,
it like linear versus second order polynomial?
well, I mean, the complex and simple, just it's the terminology that Wilms used. So nested model is really what we generally, the term we generally use. So in other words, when one model is a special case of the other model. The complex model, so if you have, like I was showing, like a line or, if you have a multiplicative term, like you multiply a power law by a cutoff, something like this, so that if you fix the cutoff to 0 or 1 or something like this, where it's now you get back the power law. The cutoff power law would be the complex, and the power law would be the simple case. But if you're testing like one physical model to another physical model, these are not nested in general.
I think there's a statistical test called the archival information criterion. Have you heard of it?
Yes.
I will talk about it.
Okay.
Yeah, it gets around this to some extent, but there's a lot of regularity conditions on that we don't honestly get to this. Yeah. Okay. So I'll let Johannes tell you what
Do you want to say something about the test?
test is just a special case of the likelihood ratio test. Avoid it. Do this.
One thing about terminology, maybe, so he was mentioning about profiling the likelihood. I use the term parametric bootstrap, or someone else was saying Monte Carlo simulation. It all means the same thing. You simulate under some null hypothesis, you generate a whole bunch of data, and you see how your analysis performs. Okay, so for model comparison, there are a couple of approaches, and so the basic idea is that you want to decide, is this model better than another model? But that's not a mathematically specific question, right? So you have to be a bit more clear what you're actually asking. And I would say there are multiple questions or situations where you have this question. One is where you have more ad hoc models, empirical models, and you're interested in whether a more complex description has more information. So you can approach this from an information content type of question when you're dealing with ad hoc or empirical models. Another criterion you might have is this empirical model better at predicting data, future data, or similar data that I currently have, or is another model better at predicting? And machine learning is using this criterion a lot with cross-validation. Another situation which we just heard about was whether there's an additional component present. So you want to test, should I add this component or not? And one approach to do this is to say, well, you might have some parameter which regulates how important that component is, for example, some normalization. And you say, well, if that parameter, let's have that axis here, the normalization, if that parameter is below some certain value, practically it's not there. So it doesn't have much of an effect. So you could have you could define a region of practical equivalence of the two models, and then all you have to do is parameter estimation, right? You say, well, is my posterior, how much of my posterior is in this region compared to that region? That is much simpler in model comparison, because parameter estimation we know more how to do than comparing between model spaces. And the third category I put up here is when you really have a set of physical models where you try to compare between physical effects. For example, Renstrahler, quantum scattering, I don't know what, or some more elaborate simulations. And one approach here is Bayesian model comparison, which I will also talk about. But that Bayesian model comparison requires that your parameters have a meaning and that you can put some priors on your parameters. And often that's the case. So let's come first to the information criteria. There are a couple, but I will talk about the Akreike information criterion. And it's really asking the question, is the more complex model worth storing? So it comes from an information background. And it's defined like this. AIC is 2 times the number of parameters minus 2 times the maximum of the likelihood. So the likelihood at your best fit. Or in CSTAT or chi² terminology, you have 2 times the number of parameters plus that value. So what it tries to balance is, well, you want, and lower AIC values are better. So it tries to balance, you have a good fit, so CSTAT decreases, and it tries to balance the complexity as measured in number of parameters. So more complex models will give you a better CSTAT, but will increase the number of parameters. Simpler model will decrease here, but go up. And then you do model comparison by looking for the model with the lowest AIC. So the advantages here are that this is rooted in information theory. It looks very simple, but actually it has quite a bit of background behind it. It's also independent of any prior distributions. The disadvantages are that you don't, so you just go by which has the higher AIC, but you don't get, is this more or less equivalent? So there are no clear thresholds one could use, although word on the street is that some values between 4 to 8 are significant AIC differences.
Sorry, just a question. You've got CSTAT in there. It's a bit like these likelihoods from Michael talking about in the previous talk. So isn't this just very similar to this likelihood ratio if you're comparing 2 different CSTATs?
It is. Yeah, it is somewhat similar, but the derivations are very different. I would say.
Yeah, I mean, yeah, the use that comes from information, but it's also in you have to be in a high number regime, so you have a symmetric posterior, and it also, I think there's a linearity in the model because of the number, the degrees of freedom.
Yeah, I should put that in the slide. Okay. Here is another way to compare models. So remember we were making these grids of parameter spaces and looking for the region which contains most of the probability. Now if you have a second model and you have its probabilities, why don't we just ask the question, is there more probability in this one than this one? And that's exactly what Bayesian model comparison does. So you compute the sum of all the likelihoods here and take the ratio to the sum of the likelihoods here. depends how you put your spacing here, and it depends how many grid points you put here compared to grid points you put here. And the first is the parameter priors, and the second, the ratio between number of grid points, is the model prior. What this does effectively is very interesting. Let's say I have one model which is very inflexible. It can only produce this kind of lines. And I have my data, and some substantial region of the parameter space kind of looks similar to the data. Okay? And then I have another model which is very flexible, let's say some polynomial, and this part of the parameter space makes this prediction, this part of the parameter space makes this prediction, and this part makes this weakly prediction. So it makes a huge diversity of predictions. And some part of the parameter space, maybe that one, looks like the data. And this likelihood will be much higher because this model is more flexible. But at the same time, because this model can produce all kinds of data, has a high prediction diversity, it produces all kinds of data shapes. Only a very small region here will look like the data. So although the likelihood here will be higher, the volume that makes something similar to the data is tiny. Whereas here, the likelihood might be a bit smaller, but the volume, the fraction of the volume in that parameter space is larger. And if we multiply the two together, which is what the summing does, we're kind of balancing the two. Also, another way of looking at this is if you add to this model a parameter that doesn't do anything, so it doesn't influence the shape, then the predictions stay the same. You just add another axis, but summing it out doesn't change anything. And so it doesn't punish by number of parameters, it punishes by prediction diversity. So I said we compute the sum over this parameter space, which is basically the integral over the likelihood over all parameters. And we call that SED. And you can compute that for one model and for the other model. And that is called the marginal likelihood. And some people also use the word evidence, although it's not really evidence because the data are the evidence, but it's a word that has one syllable benefit over the other word. And then you have this averaged likelihood, which again for complex models is being pushed down, and take the ratio to the other average likelihood, marginal likelihood. And that is called the base vector. So that should tell you which model is currently being preferred by those data. And it's also, I deleted this here, but when I wrote Bayes' theorem, I wrote this. The posterior here, and here we have the prior and the likelihood, and here we have this normalizing constant. And we were making this normalizing constant so that this is normalized to 1 over the parameter space. We were integrating over the parameters, and that is just that integration constant over all of the parameters. So this is what we're looking for here to compare models, and if we take the ratio, that's called the Bayes factor. And because this is probability of the data of one model, but not the probability of the model given the data, we do the same trick that you already know. We do this to get, in the end, the probability of the model given the data. And we do that for 1, So that's just what I wrote here. The base vector, the prior odds ratio is the first term, which is your initial preference for one model over the other. You might set that to 1 if you want. And then you have the posterior odds here, which is how much more probable that model is compared to that model. If you have more than 2 models, you just take the sum here, then you get the probability of that specific model compared to all of the other ones, and it works the same. Now, again, it's kind of similar to parameter estimation. You find, in parameter estimation, you found regions of the parameter space where most of your probability are. Here you find, out of your set of models, where most of your probability is after this normalization. So you prefer some models and you throw away the ones where there's basically no probability. Now there are 2 things I want to emphasize here. One is, if we throw out some models, we're making a decision. And we can make false decisions in one way or another way. And we want to know what is our rate of making wrong decisions. And so also, this is expressed here in another way, if the probability of one model compared to the other model is 3 to 1, does that mean M2 is correct in that ratio? To understand that, just skip over that. To understand that, because we want to take these model probabilities, make decisions, and want to characterize the false decision rate, understand how many false positive or false negatives we have, again, I would recommend to do simulations. So basically the idea is you simulate under one model, and look how many times you falsely choose the other model. And you simulate under the other model and see how falsely you would select the first model. Here's an example where I did that. And now that Joern is gone, I can use WAPs. And here I simulated with a power law and counted how many times the absorbed power law is selected. And here I put in an absorbed power law and saw how often the power law alone is selected. And if I take some base factor threshold, I can count my false negative rate that's shown here in red. So you want to look at both of those terms together. And if I use a base factor ratio of larger than 2, basically I have no false negatives. But again, for some data sets, I might not make a decision because it's not going by a factor of 2 in one direction and not in the other direction. They're about equal, so I wouldn't prefer one model over the other. And that's kind of an interesting property of the method that tells you, I don't know. And here I compare 2 likelihood ratios. Again, this is profiling the likelihood, simulate on the one data set, see how many times I would prefer the other one under some likelihood ratio threshold. That's plotted here. And if you take the 2 together, and you would choose Wilks' theorem, you would be here, and you see that the false negative rate is higher than what you can achieve here. So that the advantages of calibrating model decisions, calibrating your base factor thresholds this way, is that you, first of all, you get rid of some prior dependencies, like model priors, but also parameter priors. And you have then frequentist properties of the Bayesian methods. That's kind of interesting. So you quantified how many times you would falsely choose something. But internally, it's a fully Bayesian treatment. The disadvantage is that you have a lot of data sets and you have to compute the integral over all of your parameter space. And that can be computationally expensive, especially if you generate thousands of data sets. So how can we do that? So here now I'm coming to this fourth category of parameter exploration algorithms, which I summarized as global global sampling, and I want to present nested sampling in particular. And the idea is the following. In MCMC and in grids, what we try to do is we have the parameter space here and the likelihood here. We try to take slices, we try to grid somehow, and get the width and the height. And then slicing it up this way, we know this part of the parameter space has this weight and so forth. Nested sampling works differently. In nested sampling, you do the integral this way. So if you imagine you have some likelihood larger than this value, sorry, smaller than this value, you have the entire parameter space, you go up, your volume shrinks, and you keep track of how much your volume shrank, and your height, and you do the integral the other way. That's called the Levenberg integral. So you're summing the shrinkage times the height as you go in this pyramid up and up. And the algorithm works as follows. You imagine your parameter space as a box. You throw in 200 points. You evaluate the likelihood. You find the one which fits the data worst, and you take it out. When you take it out, the idea is if you sorted all of your values, if you take one out, the volume you're looking at is suddenly 1 over 200 smaller. And now because you don't want to run out of points, you throw in a new point, again, according to your parameter volume. You throw in a new point under the condition that it's a better fit than that one. It has to be uniformly again in that space, but if it's a worse fit, you try again. And that, in every iteration, makes the volume shrink by a constant factor, which is basically this. And so you're keeping track of the shrinkage and the height, because that's the likelihood of the point you just threw out, and that allows you to make that integral. And that gives you the total integral over the parameters. And as you proceed, initially you have points everywhere, but you throw points out and put new ones in. It kind of zooms into the region of the higher and higher likelihoods. And at some point, it's going to have a volume that's very tiny, and the volume is going to be very small, so it's not going to contribute to that sum, and at that point you can stop. So there's a natural convergence point, a finishing point to this algorithm. The drawback is that you have to find a way to sample new points that give you a better fit than the one you just threw out. And that, putting that part in is the difficult part. But some solutions have been developed for that. So for MCMC, you have to put in this jumping point. For nested sampling, there are some general solutions. One is to do MCMC inside, but the one I will talk about is to use multi-nested inside. And how does that work? Well, we already have a whole bunch of points that fulfill our likelihood constraint. So we should take advantage of this knowledge of the space, of the parameter space, that is probably where we will find our new point. So the idea of these two algorithms is to build a region around these points and sample from that region rather than from the entire parameter space. And what multiness does is it clusters these points into hyperellipsoids, and then it samples from these ellipsoids. And this turns out to be quite robust and sample very efficiently. And then you can do both parameter estimation and model comparison, because it gives you both posterior samples and that integral over the parameters. And I will show you an animation of another algorithm which builds regions, ellipsoids basically around each point. Slightly different, but gives you the same idea. So it starts out with all of these blue points everywhere, and it builds the green region, which in the beginning has everything. But you see the green region is all spheres or circles around those points. And it's going to try to draw a new point inside. And it always takes out one point, which is the worst fit, which you start to see now. So it's always where the arrow starts from. And the blue points, which are the live points, the ones that are currently fulfilling the threshold, are tracing out the distribution we're sampling. And we try to draw new points from the screen space. Sometimes it makes a bit of a mistake, but then after a while, hopefully it finds back. And that's the idea. And then if we let it run a bit faster, it goes to higher and higher contours of this likelihood. So it walks up that hill, and the volume gets smaller and smaller, and then at some point we have seen the entire parameter space. At the same time, it keeps track of the points it visited and can build these probability distributions and stop at them. So nested sampling gives you both weighted posterior chains and this evidence with which you can do model comparison like that. Okay, so here is a very subjective. Did you want to jump in at some point, or
Yeah,
okay. So right, I will point to you right now. So very subjective how you should approach model comparison from my point of view, but everyone has different opinions. It matters if you're testing a model in isolation. So you just have one model and you want to know, is this a good fit? Goodness of fit is a word. What is its mathematical meaning? I'm not sure. But if you want to see if that model could produce your data, you want to do posterior predictive checks or parametric bootstraps to see how well it performs and if what it produces looks like your data. If you compare multiple models, then you have to ask the question, are they empirical models or more physical models? If you have empirical models, I would go to something like information criteria or cross-validation for its prediction quality. But if you do physical models, then it depends if you do nested models or not. You might do something like regions of equivalence or just parameter estimation. But in both cases, you could do Bayesian model comparison. And that leaves me to you to hand over to line detection in particular and posterior predictive.
Yeah, and I'll just say one more thing from we're non-statisticians. It seems if you read what's going on in the stats literature, the modern stuff, it's theory behind model comparison in an open setting when you don't when one of the true models is not in there is kind of an open question. So there are statisticians that would say we don't know how to compare models yet. Like so some of these tools. So it's a fun read and it's important to go to the statistics literature to see some of these things and understand the exact problem you want to ask.
You were talking about Bayes factors, but you didn't talk about the ratio of BH1 and BH0. So the other term. Yeah, or BM1 and BM2. What do you do about the prior odds ratio?
Yeah, so what I was showing with the calibration is you try to make a decision on the ratio of this, and you calibrate it so that you don't make false decisions very often. But calibrating this ratio, if you have a constant here, is equivalent to calibrating this ratio. So then you kind of escape the whole thing of defining this. But in other cases, you might have prior odds for one model or the other. For example, if you want to compare whether the source is detected or not, it's going to depend on, say for example, you have a field observation and you have a whole bunch of objects in there. Whether that particular object belongs to some object class, like supernova remnants, for example, also depends on how frequent you expect supernova remnants. Maybe they don't exist in the universe, then your prior odds are very low. But if they are all abundant in that particular region, then the prior odds should be high. So you can put in here information about your survey, for example. What's its depth and how often would you expect one case to be true or not. So these can actually be well justified in some cases. But yeah, in other cases it's difficult to define, and that's where I would choose the calibration step.
Like faster than light neutrinos. You have a pretty good model prior for that.
You had another question, yeah?
Yeah, it's really like the multi-net. How it robust is against multi-local minima?
Oh, it's very robust. Actually, that's one of the motivations why it was created. So, two things. Because you start out with putting samples in the entire parameter space, it is a global search algorithm, and it shrinks down, walks up the hills from everywhere. That kind of makes you more robust against missing some nodes. And the other part is that because it defines the regions around the points that you already have, and it splits the regions by clustering, it's efficient even if you have many nodes. And that's actually one of the reasons why it was there.
I suppose that for given dimension of your problem, you have a minimum amount of points that you have to spread over your entire space so that actually you don't miss a corner. If, for example, you're lucky and then your minimum is actually on the corner of the parameters space.
Yeah, so it turns out, at least in practice, that it doesn't depend so much on the dimensionality. But when you throw in the points, and because you always take out one and throw in, you kind of slowly wandering towards the important regions. And so you only need one of those points to kind of hit the foot of a hill. And as soon as you get kind of the starting point of that hill, you will kind of start to zoom in there, and there will be new points in that vicinity being placed. So you don't have to hit the peak of the hill, but it helps if all the other points kind of guide you towards that direction.
You have a very high dimensional parameter space in small regions where it fits good.
Yeah, so this method, because it works with neighborhoods, and neighborhoods don't work well in high dimensions, it starts to work very inefficiently starting at 20 dimensions, let's say. But on the other hand, nested sampling is nice because it shrinks by a constant factor, so it zooms into smaller and smaller and smaller and smaller regions, so you exponentially go to the parts that are actually interesting.
So, really nice and interesting. Can it be parallelized, or you have to choose one at a step at a time?
It is, you can parallelize it, and one of the reasons you can parallelize it is because you kind of draw from these extended regions. You try to find a new point above that threshold, and that can be quite inefficient. So you just draw a whole bunch of points and spread it out over a course, parallelize it that way, and until you have actually hit one. And so that, in that sense, it is easy to parallelize.
It is.
And it is, so an implementation I have is EXA, which script with MPI. You can run it on a cluster, and it will do that parallelization for you.
But if you have a fast likelihood, a lot of times the parallelization doesn't really help you because there's some work that you have to do in the background. Sometimes it's more costly to open up threads. But yeah, one more thing is just again for writing things in papers, you have to be really careful. I've seen people saying that are using nested sampling and say MCMC, and it's not an MCMC algorithm. It's not a Markov chain. It's a completely different sampling algorithm. It's important because if you see, people calculate, saying, "Oh, I calculate the evidence with MCMC," that's almost impossible. So it's important to know that they're completely different algorithms. And when you write in papers, you use one of those algorithms to specify exactly which one you use.
More questions?
Okay, so just as a follow-up to the model comparison in general, quick treatise component detection, which it's good to hear that some of you guys are familiar with this Burgess paper, which is talking about specifically the failability. In fact, I just noticed last night the short title for this paper, if you never noticed before, is the fallible F-test. But the point of this paper that came out was people were using likelihood ratios to test for model components. Now, naively, right? Naively, if you're looking for, say, I have my function is some continuum spectra G of X plus a line or an additive component, right? Where
You have to write slightly larger.
yeah.
On the last row, sorry.
Is this? Yep. Yeah. Here we go. Sorry, I hate erasing Bayes' theorem. Okay, so if I had some spectrum and it was still writing too small. Some continuum, right? A line, or a line parallel, whatever, and then some additional component that is, could be a Gaussian line or a black body component, whatever. That's parameterized by normalization multiplied by some shape. Okay, this is a component, and this parameter is bounded to be positive. Okay, this is not a nested model. It's naively you would say, oh, if I just set this to 0, it's fine. The problem is that the nestedness, which comes back to the symmetry that we were talking about earlier, Wilms theorem. The nestedness means this parameter has to be able to go positive and negative, and physically, an additive component can't do that. And so, Prozov and Van Dyke and some other statisticians, there's Nita, who's from Chow, and these are a really good group from computer.
Sorry, why cannot be positive and negative? Imagine that you are adding to a continuum an H beta line. It can be an addition or an absorption, so it can be.
In that case, that's
so in that
fine.
case, it would
yes,
be okay.
Right.
Okay.
So the specificity of this is that this parameter must be unbounded.
Okay.
Not if it's not, then it's okay. But if you are looking for an additional component,
okay,
the F-test will, likelihood ratio test will fail. We also have this same thing in gamma reverse, so people like to add on a bunch of additional additive components and then try to compare and see how significant they are. And they also just use the likelihood ratio test, and we found out that we actually go and profile the likelihood. They were finding components that are significant at the 5 sigma level. And sometimes these curves that I was showing you earlier when we profiled Wilms theorem, they're not necessarily monotonically decreasing. If you go out far enough and you try to go up to the 5 sigma level, they start creeping back up. It's just because these aren't formally nested models. So you can't actually use the likelihood ratio test. Now, in Protosolve, they went out and these are the same kind of things I was showing you earlier. They went in and tested these on a bunch of simulations, and they find out that you get these weird distributions in some cases. Sometimes it doesn't actually look like a chi², falls off too fast, or it has a completely different shape. And so the main point of that paper was if you're going to do any type of component detection where the parameter is bounded, you need to go to a different technique than the likelihood ratio test. And they specifically motivate in that paper to do Bayesian model comparison. And I like the very last line is it's not only that you might overpredict or underpredict the component, but there's no guarantee, since most of the time when they were doing all the tests in the Protosolve, they were using simulated data, so it's a perfect situation. Data are never perfect. There's going to be all kinds of pathologies in them. And so there's no guarantee that even some of the conditions they found when they fixed the likelihood ratio test, that it will actually work. So they really advocate for doing something like Bayesian model comparison, which doesn't, in general, have the same type of pathologies that a likelihood ratio test has. So if you're looking for lines or additional components that are bounded for their normalization component, you need to use something like Bayesian model comparison. It's just safe. So it kind of goes back to this likelihood ratio. Any questions about that?
Well, this only applies if it's bounded.
Yes.
So if I look at a spectrum, I see a line, I fit it, but I also allow it to go negative. And I fit it unbounded. So there's something in my procedure that's changed the result, maybe I'm seeing the line.
Yeah, I mean, I thought about this as well. I don't really know what the answer to that question is. Again, you get around this in Bayesian model comparison by putting a prior that it's positive. That's one of the different things. Yeah, and if you bound, as Joern was saying, if you bound in maximum likelihood of the parameter, you actually screw up the descent and the statistics and everything. So, yeah, you could allow that to be true, but of course then you have weird confidence ranges, right? Especially if it's very weak. So yeah, I mean the summary is always should calibrate whatever test, which leads us to Wilms fit. Or well, actually, no.
So the other point you could run into is if you allow it to be negative, your model can predict negative count rates. That then doesn't make any physical sense if that A is allowed to be negative.
I guess it's a very strong line, isn't it?
Well,
it's very challenging.
What I also wanted to say is that boundedness is the issue that the parameter spaces cannot go there, or is the issue that again you have this Gaussian assumption and the Gaussian has to be away from it?
So you can look at it from that. So it can be a bit heuristically looked at with the assumption of the shape there. The way that if you go through the paper in Protosolve, it has to do with set theory. Yeah, it's a quite involved proof, but it's about the openness of the set on the boundary, and it's a very fun paper, but I don't really understand most of that, so you just shouldn't do it.
And you were saying you would recommend Bayesian model comparison, but maybe my question is already answered with your kind of summary slide, calibrate, but wouldn't you agree that you can also do simulations and look at the likelihood ratio test and see how often look at the distribution of likelihood ratios?
Yeah, you can, but the problem is that you can actually find, I mean, this is what we found there as well, is that because that's not really a nested model, you won't necessarily find a monotonically decreasing function never can be sure that it won't, this thing won't increase, and then the whole idea of significance goes up.
Yeah, and I guess this is something which I'll do another point for like Bayesian approaches in there, but especially those who have done high resolution spectroscopy, you usually have a lot of trials on the lines, and partly trials that come from the data. If I see a selecting line in high resolution channel rate TG spectra, I'm going to expect a lot of other selecting lines and so on. So kind of doing significances there, I think it's, from what I know, is almost still an unsolved problem globally.
Yes. I mean, significance is a decision theory thing, and yeah, for me, I just look at the distribution of the parameter. I don't make a decision, and the truth is there, right? Is that it's this probable that the line is this high. That's it's uncomfortable because our brains are tuned to make decisions, but it's scientifically more robust. Okay, so to wrap up today, we will talk about goodness of fit, and then work into PPCs. And I'll start out with one of my favorite papers. I don't know if any of you if you're on Facebook, if you're a member of the astrostatistics group. It's one of the reasons I got really into astrostatistics. It's an awesome place to go ask questions. This is probably the most posted paper there when someone goes, oh, I want to do this, and my degrees of freedom are that for chi², blah, blah, blah. This paper just gets posted almost every single time. And the reason is because it's an amazing paper that tells you don't use reduced chi². Even with when you're actually you have a Gaussian, like it's a really bad quantity that was again derived. It applies to this really simple case of a linear model with a Gaussian likelihood and really nice, bright, or abundant data. I won't go through everything in this paper, but I really encourage you to because there's so many pitfalls that that you can run into. But one of the first ones is really about this concept of degrees of freedom, because people, even if you're not using chi², you'll see sometimes you'll see C-stat for degrees of freedom. Oh, it's 1, so everything is great. The problem is that the concept of degrees of freedom only works out for linear models, or models that are linear in their parameters, which we'll talk about in a moment. Well, this is what that means, is that the parameters here, theta1, theta2, they can be multiplied by other functions as long as those functions aren't dependent on parameters themselves. So a polynomial, for example, is a linear model because it's linear in its parameters. To get to chi², we can set up this equation. This is our general model. We can have our measurements be this kind of vector, and this is just another way to write chi². It's just a matrix equation with these squares, right? And then we want to optimize this, so we take the derivative of that. Joern's been through all this, give us our best parameters, and it leads us to the latent data, which is proportional to this matrix H here. And what the formal definition of degrees of freedom is the rank of that design matrix. Okay, so at best, if the design matrix is full rank, in other words, it's a linear model, then the number of degrees of freedom is equal to the number of data points minus the number of parameters. Any other time, it's not. And I can show you a pretty simple example of where this falls apart. How many free parameters are there in this model? Where X is the data space, or the space.
So I think you want the answer 6, right?
Yeah, sure.
But I think there are addition theorems with which
And that's what the rank of this matrix is telling of the design matrix. And so if you were to use degrees of freedom for a function like this and say, oh, it's near 1, it becomes actually a meaningless number. And that's why these types of measures for goodness of fit, especially for the nonlinear functions that we use in X-ray spectroscopy, we shouldn't be quoting our statistic versus the number of degrees of freedom because it's not a correct term. And a value being close to 1 or not really doesn't have any meaning. And another important thing about that is that when we quote values of reduced chi², we like to use the magnitude of how far it is from 1. But when you run into situations like this, that magnitude, the difference between 1.1 and 2.6 can be very big or can be very small. But since there's no well-defined theory for measuring that magnitude, which we will use to put a value on the quality of the fit, it makes those numbers completely meaningless. But that's okay. That's just when we're using a Gaussian likelihood. This gets much worse when we have things like Poisson data where you shouldn't be using chi² in the first place. So the bottom line is that we should not be using reduced chi² at all, or reduced C-stat, or any of these values to be quoting goodness of fit. Which the idea of goodness of fit is like it's a within model check, right? How good? The question we want to ask is, did this model generate our data, right? Or could we generate future data, right, from this model that look like the data that we have? Now, there are some other types of things that people have come up with, like Andrew Gelman. There's things called like Bayesian p-values, Bayesian tell probabilities, where you use the posterior. The problem with those, as Gelman has pointed out, is that the idea there is that if you look at the p-value, it should be about 0.5, because it should be the comparison between the model and the data should look like future realizations. But he found two very simple cases where these p-values weren't actually uniformly distributed. So even going to Bayesian statistics or Bayesian probability theory and trying to reduce tell probabilities there's no guarantee that any value that you derive is a useful value. Because you can find situations where the assumptions, such as that the p-value is uniformly distributed, break down. So you have to be kind of careful with that. So that's what's kind of led people to start looking at something called the posterior predictive distribution and posterior predictive checks. I'll tell you right off that they're immediately unsettling because I hate things like chi². But at the moment, because of the lack of well-defined and theoretically robust model checking tools, visual inspection of posterior predictive distributions are some of the most robust things that we have that we can use for checking data, especially in Bayesian. So one of the things that people like to do in the maximum likelihood framework is to look at residuals, right? And a residual is just kind of a distance measure between the observed value of the data, which has perhaps been obscured by some sort of measurement error, and so we sampled our observed data point, which is what our likelihood is telling us, from some latent true data point. And if you compute the distance between that, that's what gives you your residuals. Now, residuals are fine in general, but if you're using Poisson data, the residuals should be Poisson distributed, not data minus model over error, which you can easily do in XSpec because it allows you to. You need to actually compute the Poisson residuals. And to do that, it's a bit of a difficult calculation. You have to use a survival function. But there's code that I've linked here, so it's some Python code to actually compute that and plot those. So if you insist on doing your model checking with residuals, make sure that you use the proper Poisson residuals and do not use Gaussian residuals for Poisson distributed data. This will be an accurate answer. So that leads me to posterior predictive checks. And they're relatively simple to compute. And the concept is pretty easy. This right here is called posterior predictive distribution. And what it is it's, here, I'm supposed to pop up. So what this is the probability of future data given the data that I've used. And that's computed by taking and integrating over the posterior and the likelihood of the data. So this is our posterior. So I've perhaps derived this through Monte Carlo sampling. I have that, and it gives me the allowed parameter space on my model, given the data that I observed. And then I go and look at the likelihood, and I generate future data from all of those distributions. Integrate over all that, and I get the probability of future data given the data that I observed, under the assumption of the model that I tested. X-ray spectrum, what does this look like? Well, here's an example in GBM, where yellow are the observed counts. And what I've done is I've taken the posterior where I've fitted, for example, here's just a smoothly broken power law. I've integrated over the posterior, and I take random points in the posterior distributed properly, and I make new data sampling from the Poisson likelihood of the data. Does that make sense? So if, I take 1 point in where I get parameter A and B from my posterior, plug that back into the likelihood with Poisson, and I draw a new value of a count, given that for each event. Okay, so this is sort of like a residual, except for a residual is looking, the residual says, okay, I take the maximum likelihood point from my parameter and the observed data point, which is a random variable, and I just compute the distance here. This integrates over both the uncertainty in the model estimates as well as the uncertainty in the data generating process. So it gives you the full picture of the variability in the model. Now, given it's a visual process, there are numerical techniques for posterior predictive checks, and like if you're just fitting a single Gaussian into like some parameter for high dimensional or something like this, where you have a whole bunch of realizations for a single spectrum. There are really numerical techniques where you can get a quantitative answer from this at the moment. So that's what it would look like for X-ray spectra. But just to go through a much more simple example, let's just fit a straight line where the error distribution is Poisson. So the green data points here, that's the true model, and the gray data points are just samples from where these data points have been drawn from a Poisson distribution. Of course, this is just one realization of the data, the one that I observed. If you were to draw different ones, you would see here these are Poisson distributed, and you see that you get integer values. Poisson distribution. Now I use Stan to fit that data with the appropriate likelihood and some priors, and you get an okay fit, not the best one because data are fragile. And you can see there the posterior mapped onto the mapped back onto the data and what the true model was. But importantly, we can also look at what the posterior predictive distribution is for this data. So by integrating over that model and the likelihood, these blue points where they're shading is indicating how their distribution, you can see that basically I'm reproducing. If I were to draw future data, it would look like the data that I actually observed, which is kind of the question that we're always after with goodness of fit. Does this model, would it generate data that looks like the data that I observed this time? We can break this down a little bit further and look at those posterior predictive checks for each data point. So you can see, the actual integer x-axis, the measured value is green, and the red value are posterior predictive realizations. You see that in general, it fits the data, which will show because I fit the true model. So that's one way of doing goodness of fit without having to rely on a lot of the assumptions that are built for other types or for very, very simple models of doing posterior predictions.
Can you learn something from the fact that for some of the observation, the value that you get has nothing to do with the distribution? Like a second row, second last column? Can you use the information for improving on your data? Or on your model, sorry?
Yes. I mean, in this case, it's just, I mean, this just shows you the fragility of why other goodness of fit techniques wouldn't work. I mean, if I were to do this thousands of times, I actually observed, I observed a rare outlier.
Yeah,
that
just
happens.
that, right? Okay.
Yeah, I mean, that's what it's doing. But if you use a point estimate, it's going to tell you, oh, this is really weird, but it actually is.
I got it.
Yeah. So, again, there is no cookbook in generic method that we can apply, especially when we have complex physical models, difficult data. As we've gone through today, we have these response matrices. There's a tower that's being built like this, but there's not really a solid foundation where we understand we do understand our instruments, but we have to model them properly. There's no base on the statistics. It's all very fragile. Special care needs to be taken, Joern said, to understand your instrument, to understand your models, to understand your data generating process. So don't use just heuristic tests, a word of mouth test, or even simple tests that are passed down traditionally. You have to go through and examine each problem in order to make sure that you don't, crack this tower somewhere and everything falls over. And the best thing you can do is read the statistical literature and make your analysis reproducible by releasing your code and your data so that other people can repeat it. And that's all I have to say about that. Questions?
Maybe if you go back one more. Yeah, here. So the idea here is that if the model was a bad fit, so if I can summarize it in a different language, for each MCMC chain point, you do fake it, you generate new data, and then you plot the data distributions and look if it lies within. And if your model, for example, if you have an emission line in there, then your model wouldn't capture that, and so the data you generate would not contain that. But the data you actually have do contain it, and you would see it here as a deviation.
Exactly. For PPCs, if your model doesn't predict data that looks like it becomes very obvious because this yellow line would not look like these shaded regions. But like you said, if there's a line in the data that you don't model, it will stick out, and your model will be able to reproduce that because it doesn't have that built in. There are lots, so as Johannes said, that's using fake it and expect is one way to do this. If you're doing any other types of analysis, fitting lines, stuff like this, there are lots of tools online, especially tools that use STAN, where you can actually, that they go through and explain PPCs, and they'll actually help you do PPCs for doing things like fitting correlations, or linear models, or different types of data. And if you stick to the literature and STAN documentation, you'll find a lot of help in understanding what PPCs are and how to use them, and some of them quantitative tests that you can apply to PPCs. It is computationally expensive.
have time now scheduled for discussions and some more questions, and I know several people have approached me and I deferred them to later, and the time of later is now, to have some more final discussions of your kind of science problems. Before that, I want to point out two more things. Tomorrow morning, what did I say when we start? 10 or at 9? 10. Okay. So tomorrow at 10, we will go into some more related issues with extended sources, calibration, and I think we'll also include a little bit of practical pointers to give you an idea how you can approach these things. But there will also be more time for you to come with your science questions, and hopefully we can be a bit more specific. And the other thing is, so at 7 we are meeting for the dinner, and I hope we can mingle across our institutes and discuss the issues we have, or just social life in general. I think many of our friends are from Rosita, but so let's see. I'm flipping the word then. Right. Daily location I already said, and I'm sure we'll group together. So, there were some more questions that people had. And one of them is already on the blackboard. Who was that? That was you. Yeah.
Yeah, so,
do you want to come out here?
Yeah. My question was about computing the mean of data with asymmetric errors. And I'm not entirely sure how to do that. So let's take a very simple example. So let's say we have a data point at 5 and the data point at 4. It's easier to calculate. Okay, so and if they have no error bars, the mean is obviously at 4 plus 2 divided by 2, which is 3, right? Okay, so now let's say we have an error bar which is 4 plus minus 2 and 2 plus minus 1. Then the weighted arithmetic mean is given by this formula, and if it's standard deviated, which in this case, let's say this is the case, it is given by this formula. So the sum of the data point divided by the error squared, and then normalize this with the error, the inverse squared error. So in this case, it would be 4 divided by 2 squared plus 2 divided by 1 squared, right? And then 1 over 2 squared plus 1 over 1 squared, which is 1 plus 2 is 3 over 1/4 plus 1 is 1.25, which is 2.4, I think. Okay, so this already changed. And now the real question is, okay, what happens if we have a data point which is 4 plus 2 minus 3?
So can I stop you?
Yes.
Yeah. So when you say data point there, so how can the likely, if it has errors like that, it means that that data point was derived from a fit, right?
Yes.
Right. So if the fit was a Bayesian fit and you had the posteriors, you would just sum together, you go through here, you would sum together, and you wouldn't worry about the asymmetry or whatever, and you would get a distribution that is whatever it is. Mm-hmm. If you have, and there's a really good book that I recently showed Johannes. If you have asymmetric errors from maximum likelihood, it means that maximum likelihood doesn't apply.
But let's take, for example, the Gaia parallaxes. I think they are asymmetric, right? But I don't know.
Did they use?
I think they are.
You can profile and compute coverage, but there is no way to propagate those. Error propagation in the maximum likelihood framework relies on the smallness and the symmetry, parabolic shape of the errors. If you don't have those conditions, you just can't move forward.
So if I encounter asymmetric errors, then something is odd in the first place.
Yes. In this book, it's called the Bayesian reasoning. I'll find the book tomorrow and post it up here. He has an entire chapter about this. He goes through and rants about how it's impossible to do anything with asymmetric errors under the maximum likelihood framework. And it's all through the high energy physics literature and everything.
Okay, so maybe I also give a shot at answering this. So there are two aspects. One is a bit of a philosophical question, and that is data don't have error bars. Would you agree?
I wouldn't.
Where do you get your error bars, Joern?
Well, I mean, it's the uncertainty of the measurement.
And how do you get that?
Well, it can be the standard deviation, for instance. Well, the scattering around the mean, for instance, if you take.
What are the error bars for Poisson measurements? Counting.
So if you have the Poisson, if you have the detector, the photon detector,
yeah, well then
you
it's
detect,
the square root.
You detect a number of photons, and this is the thing we know, and we call data. There's no uncertainty on that. That's actually the thing. That's the only thing you know.
Yeah. Okay.
Similarly, if you do another measurement with the complex machinery, you might understand well how that behaves, and you get some scatter in how reliable that measurement is. But you do get a measurement, and the rest of the error bars is a model of that machinery. So it describes some model behavior. And if you project everything in data space, usually the answers are much simpler. So coming to this example, what you're encoding here is that you have some value which you trust with some probability distribution.
Yeah.
So if I may plot this on top of here, what you're essentially saying is that you have a Gaussian probability distribution that is kind of summarized by these two numbers.
Exactly. Yeah.
And what you're then trying to do is you're assuming the model that both of these data points come actually from the same process. So you're assuming there's a constant here which describes both data points, and you try to fit that. And if you write down the Poisson, the Gaussian probability, you write the first point with its first uncertainty squared, and then the second point with the same value, because that's what you're varying, with its uncertainty squared. That's kind of the probability that you're trying to get out. That will again give you a probability distribution. And then you can show that that probability distribution, if those two are Gaussian, is again a Gaussian. And that's where these rules come from.
Yeah.
Now, if you have this scenario, you're describing not a Gaussian distribution.
Yeah.
You're describing something else.
Yeah. So one would have to go back to the raw data.
Well, that would be ideal, but not necessarily. You could also write, instead of multiplying the Gaussian probabilities, you could assume again a constant. You have the probability distribution that you encode somehow. For each value, you could describe its probability, and then you vary that, and again, you get a probability distribution out, which will not look Gaussian, but will look
Okay. Yeah, well, this is an extreme example where some are like, well, sometimes the error bar is larger above the value and sometimes it's smaller. Maybe most of the time it kind of looks the same, and then one can approximate how the probability distribution looks like. Okay, all right, thanks.
So at least someone else with another question. Or any other questions? Or everyone is tired? Yeah? So, let's leave here. For the restaurant, are you coming or are you dead? Are you dead or are you coming to the restaurant? Oh, awesome. So, what do you say, 6:15? Is that your time? Yeah, let's meet outside the institute at 6:15. To travel there, or otherwise, if you